Do you know, humans have a lot of misconceptions about machine learning. Many say using machine learning, humans can do time travel. Machine learning is not a magic. The term machine learning is everywhere these days, from self-driving cars to voice recognition software and robotic activities. The study of machine learning focuses on software that can learn from examples. The growth in technology has led to increasing demand for professionals who can understand and use the vast amount of data every day. Companies like Facebook, Google, Tesla, and many more are constantly hiring machine learning professionals with salaries going as high as $250,000. Today, we present you the machine learning full course. We will begin with the fundamentals of machine learning and walk you through the advanced machine learning concepts and algorithms used in the process. We will be briefing you with a detailed introduction to machine learning that covers the sources of data, types of machine learning, and applications. Post that, we will dive deep into understanding the fundamental differences between AI, ML, and deep learning, as they all have similar roles and responsibilities. Proceeding with the course, we will teach you different machine learning algorithms with hands-on demo explanations in Python. Up ahead, we will get into applications of machine learning. Proceeding, we will walk you through some amazing projects like fake news detection, object detection, and mask detection. These projects will serve you as the finest portfolios for your future interviews. Speaking of interviews, we have covered you along with the most frequent asked machine learning interview questions to help you crack the toughest interviews. If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind, or to our training experts.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and the wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
Here we have our, it looks a little bit like Frankenstein, our Frankenstein-looking robot. Today, let me tell you what is machine learning. Machine learning works on the development of computer programs that can access data and use it to automatically learn and improve from experience. Watch a robot builder construct a house in 2 days. This was back in July 29th, 2016, so that's pretty impressive. This amount of time to continue to grow in its development. And it's smart enough to leave spaces in the brickwork for wiring and plumbing, and can even cut and shape bricks to size. Amazon Echo relies on machine learning, and with more data it becomes more accurate. Play your favorite music, order pizza from Domino's, voice control your home, request rides from Uber. Have you ever wondered the difference between AI, machine learning, and deep learning? Artificial intelligence, a technique which enables machines to mimic human behavior. This is really important because this is how we are able to gauge how well our computations or what we're working on works, is the fact that we're mimicking human behavior. We're using this to replace human work and make it more efficient and make it more streamlined and more accurate. And so the center of artificial intelligence is the big picture of all of this put together. IBM Deep Blue Chess, electronic game characters. Those are just a couple examples of artificial intelligence. Machine learning, a technique which uses statistical methods, enabling machines to learn from their past data. So this means if you have your input from last time and you have your answer, you use that to help prove the next guess it makes for the correct answer. IBM Watson, Google search algorithm, email spam filters, these are all part of machine learning. And then deep learning, which is a subset of machine learning, composing algorithms that allow a model to train itself and perform tasks. AlphaGo, natural speech recognition. These are a couple examples. Deep learning is associated with tools like neural networks where it's kind of a black box. As it learns, it changes all these things that are, as a human, we would have a very hard time tracking. And it's able to come up with an answer from that. Now let's see how machine learning works. First, we start with training the data. Once we've trained the data, we go into the machine learning algorithm, which then puts the data into a processing, which then goes down to another machine learning algorithm. And then we take new data, because you have to test whatever you did and make sure it works correctly, and we put that into the same algorithm. Once we do that, we check our prediction, we check our results, and from the prediction, if we've set aside some training data and we find out it didn't do a good job predicting it, and it gets a thumbs down as you see, then we go back to the beginning and we retrain the algorithm. And a lot of times it's not just about getting the wrong answer, it's about continually trying to get a better answer. So you'll see the first time you might be like, oh, this is not the answer I want, depending on what domain you're working in, whether it's medical, economical, business, stocks, whatever. You try out your model, and if it's not giving you a good answer, you retrain it. If you think you can get a better answer, you retrain it, and you keep doing that until you get the best answer you can.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
Human versus artificial intelligence. Humans are amazing. Let's just face it, we're amazing creatures. We're all over the planet. We're exploring every niche and nook. We've gone to the moon. We've gone into outer space. We're just amazing creatures. We're able to use the available information to make decisions, to communicate with other people, identify patterns in data, remember what people have said, adapt to new situations. So let's take a look at this. So you can get a picture. You're a human being, so you know what it's like to be human. Let's take a look at artificial intelligence versus the human. Artificial intelligence develops computer systems that can accomplish tasks that require human intelligence. So when we're looking at this, one of the things that computers can do is they can provide more accurate results. This is very important. Recently I did a project on cancer where I was identifying markers. And as a human being, you look at that and you might be looking at all the different images and the data that comes off of them and say, I like this person, so I want to give them a very good outlook. And the next person you might not like, so you want to give them a bad outlook. Well, with artificial intelligence, you're going to get a consistent prediction of what's going to come out. Interacts with humans using their natural language. We've seen that as probably the biggest development feature right now that's in the commercial market that everybody gets to use, as we saw with the example of Alexa. They learn from their mistakes and adapt to new environments. So we see this slowly coming in more and more. And they learn from the data and automate repetitive learning. Repetitive learning has a lot to do with the neural networks. You have to program thousands upon thousands of pictures in there, and it's all automated. So as today's computers evolve, it's very quick and easy and affordable to do this. What is machine learning and deep learning all about? Imagine this. Say you had some time to waste. Not that any of us really have a lot of time anymore to just waste in today's world. And you're sitting by the road, and you have a whole lot of time passes by. There's a few hours. And suddenly you wonder, how many cars, buses, trucks, and so on passed by in the 6 hours? Now, chances are you're not going to sit by the road for 6 hours and count buses, cars, and trucks, unless you're working for the city and you're trying to do city planning, and you want to know, hey, do we need to add a new truck route? Maybe we need a bicycle lane because we have a lot of bicyclists here, that kind of thing. So maybe city planning would be great for this. Machine learning. Well, the way machine learning works is we have labeled data with features. Okay, so you have a truck or a car, a motorcycle, a bus, or a bicycle, and each one of those are labeled. It comes in, and based on those labels and comparing those features, it gives you an answer. It's a bicycle, it's a truck, it's a motorcycle. Let's look a little bit more in depth on this. In the model here, the features we're looking at would be like the tires. Someone sits there and figures out what a tire looks like. It takes a lot of work. If you try to figure the difference between a car tire, a bicycle tire, a motorcycle tire, so in the machine learning field, this could take a long time if you're going to do each individual aspect of a car and try to get a result on there. And that's what they did do. That was this is still used on smaller amounts of data where you figure out what those features are and then you label them. Deep learning. So with deep learning, one of our solutions is to take a very large unlabeled data set and we put that into a training model using artificial neural networks. And then that goes into the neural network itself when we create a neural network. And you'll see the arrows are actually kind of backward, but which actually is a nice point because when we train the neural network, we put the bicycle in and then it comes back and says, if it said truck, it comes back and says, well, you need to change that to bicycle. And then it changes all those weights going backward, they call it back propagation, and let it know it's a bicycle, and that's how it learns. Once you've trained the neural network, you then put the new data in, and they call this testing the model, so you need to have some data you've kept off to the side where you know the answer to. And you take that and you provide the required output, and you say, okay, is this neural network working correctly? Did it identify a bike as a bike, a truck as a truck, a motorcycle as a motorcycle? Let's just take a little closer look at that. Determining what objects are present in the data. So how does deep learning do this? And here we have the image of the bike. It's 28 by 28 pixels. That's a lot of information there. Could you imagine trying to guess that this is a bicycle image by looking at each one of those pixels and trying to figure out what's around it? And we actually do that as human beings. It's pretty amazing. We know what a bicycle is, and even though it comes in as all this information. And what this looks like is the image comes in, it converts it into a bunch of different nodes. In this case, there's a lot more than what they show here. And it goes through these different layers and out comes and says, okay, this is a bicycle. A lot of times they call this the magic black box. Why? Because as we watch it go across here, all these weights and all the math behind this, and it's a little complicated on the math side. You really don't need to know that when you're programming or working with the deep learning. But it's like magic. You don't know, you really can't figure out what's going to come out by looking what's in each one of those dots and each one of those lines are firing and what's going in between them. So we like to call it the magic box. So that's where deep learning comes in. And in the end, it comes up and you have this whole neural network. It comes up and it says, okay, we fire all these different pixels and we connects all these different dots and gives them different weights. And it says, okay, this is a bicycle. And that's how we determine what the object is present in the data with deep learning. Machine learning. We're going to take a step into machine learning here, and you'll see how these fit together in a minute. The system is able to make predictions or take decisions based on past data. That's very important for machine learning, is that we're looking at stuff, and based on what's been there before, we're creating a decision on there. We're creating something out of there. We're coloring a beach ball. We're telling you what the weather is in Chicago. What's nice about machine learning is a very powerful processing capability. It's quick and accurate outcomes, so you get results right away. Once you program the system, the results are very fast. And the decisions and predictions are better. They're more accurate, they're consistent. You can analyze very large amounts of data. Some of these data things that they're analyzing now are petabytes and terabytes of data. It would take hundreds of people hundreds of years to go through some of this data and do the same thing that the machine learning can do in a very short period of time. And it's inexpensive compared to hiring hundreds of people. So it becomes a very affordable way to move into the future is to apply the machine learning to whatever businesses you're working on. And deep learning. Systems think and learn like humans using artificial neural networks. Again, it's like a magic box. Performance improves with more data. So the more data the deep learning gets, the more it gives you better results. It's scalability. So you can scale it up, you can scale it down, you can increase what you're looking at. Currently, we're limited by the amount of computer processing power as to how big that can get, but that envelope continually gets pushed every day on what it can do. Problem solved in an end-to-end method. So instead of having to break it apart, and you have the first piece coming in and you identify tires, and the second piece is identifying labeling handlebars, and then you bring that together that if it has handlebars and tires, it's a bicycle, and if it has something that looks like a large square, it's probably a truck. The neural networks does this all in one network. You don't really know what's going on in all those weights and all those little bubbles, but it does it pretty much in one package. That's why the neural network systems are so big nowadays and coming into their own. Best features are selected by the system. And this is important. They kind of put it's on a bullet on the side here. It's a subset of machine learning. This is important. When we talk about deep learning, it is a form of machine learning. There's lots of other forms of machine learning, data analysis, but this is the newest and biggest thing that they apply to a lot of different packages, and they use all the other machine learning tools available to work with it. And it's very fast to test. You put in your information, you then have your group of tests, and then you held some aside, you see how does it do. It's very quick to test it and see what's going on with your deep learning and your neural network. Are they really all that different? AI versus machine learning versus deep learning. Concepts of AI. So we have concepts of AI. You'll see natural language processing, machine learning, an approach to create artificial intelligence. So it's one of the subsets of artificial intelligence. Knowledge representation, automated reasoning, computer vision, robotics, machine learning versus AI versus deep learning, or AI and machine learning and deep learning. So when we look at this, we have AI with machine learning and deep learning. And so we're going to put them all together. We find out that AI is the big picture. We have a collection of books. It goes through some deep learning. The digital data is analyzed. Text mining comes through. The particular book you're looking for, maybe it's a genre of books, is identified. And in this case, we have a robot that goes and gives a book to the patron. I have yet to be at a library that has a robot bring me a book, but that will be cool when it happens. So we'll look at some of the pieces here. This information goes into, as far as this example, the translation of the handwritten printed data to digital form. That's pretty hard to do. That's pretty hard to go in there and translate hundreds and hundreds of books and understand what they're trying to say if you've never read them. So in this case, we use the deep learning because you can already use examples where they've already classified a lot of books, and then they can compare those texts and say, oh, okay, this is a book on automotive repair. This is a book on robotic building. The digital data is then analyzed. Then we have more text mining using machine learning. So maybe we'd use a different program to do a basic classify what you're looking for and say, oh, you're looking for auto repair and computers. So you're looking for automated cars. Once it's identified, then of course it brings you the book. So here's a nice summation of what we were just talking about. AI with machine learning and deep learning. Deep learning is a subset of machine learning, which is a subset of artificial intelligence. So you can look at artificial intelligence as the big picture. How does this compare to the human experience in either doing the same thing as a human we do, or it does it better than us? And machine learning, which has a lot of tools, is something that learns from data, past experiences. It's programmed. It comes in there and it says, hey, we already had these 5 things happen. The 6th one should be about the same. And then there's a lot of tools in machine learning, but deep learning then is a very specific tool in machine learning. It's the artificial neural network, which handles large amounts of data and is able to take huge pools of experiences, pictures, and ideas and bring them together. Real life examples. Artificial intelligence, news generation. Very common nowadays as it goes through there and finds the news articles or generates the news based upon the news feeds or the backend coming in and says, okay, let's give you the actual news based on this. There's all the different things. Amazon Echo, they have a number of different Prime Music on there. Of course, there's also the Google Command, and there's also Cortana. There's tons of smart home devices now where we can ask it to turn the TV on or play music for us. That's all artificial intelligence. From front to back, you're having a human experience with these computers and these objects that are connected to the processing. Machine learning, spam detection, very common. Machine learning doesn't really have the human interaction part. So this is the part where it goes and says, okay, that's a spam, that's not a spam, and it puts it in your spam folder. Search engine result refining, another example of machine learning, whereas it looks at your different results and it is able to categorize them as far as this had the most hits, this is the least viewed, this has 5 stars, however they want to weight it. All good examples of machine learning. And then the deep learning. Deep learning, another example is as you have like a exit sign, in this case is translating it into French, sortie. I hope I said that right. The neural network has been programmed with all these different words and images, and so it's able to look at the exit in the middle, and it goes, okay, we want to know what that is in French, and it's able to push that out in French, and learn how to do that. And then we have chatbots. I remember when Microsoft first had their little paperclip. Boy, that was like a long time ago. They came up and you would type in there and chat with it. These are growing. It's nice to just be able to ask a question and it comes up and gives you the answer. And instead of it being where you're just doing a search on certain words, it's now able to start linking those words together and form a sentence in that chat box. Types of AI and machine learning. Types of artificial intelligence. This and the next few slides are really important. So one of the types of artificial intelligence is reactive machines. Systems that only react. They don't form memories, they don't have past experiences, they have something that happens to them and they react to it. My washing machine is one of those. If I put a ton of clothes in it and they get all clumped on one side, it automatically adds a weight to recenter it. So that my washing machine is actually a reactive machine working with whatever the load is and keeps it nice, and so when it spins it doesn't go thumping against the side. Limited memory. Another form of artificial intelligence. Systems look into the past. Information is added over a period of time and information is short-lived. When we're talking about this and you look at like a neural network that's been programmed to identify cars, it doesn't remember all those pictures. It has no memory as far as the hundreds of pictures you process through it. All it has is, this is the pattern I use to identify cars as the final output for that neural network we looked at. So when they talk about limited memory, this is what they're talking about. They're talking about, I've created this based on all these things, but I'm not going to remember any one specifically. Theory of mind. Systems being able to understand human emotions and how they affect decision making to adjust their behaviors according to their human understanding. This is important because this is our page mark. This is how we know whether it is an artificial intelligence or not. Is it interacting with humans in a way that we can understand? Without that interaction, it's just an object. So when we talk about theory of mind, we really understand how it interfaces. That whole, if you're in web development, user experience would be the term I would put in there. So theory of mind would be user experience. How is the whole UI connected together? And one of the final things is, as we get into artificial intelligence, is systems being aware of themselves, understanding their internal states, and predicting other people's feelings and act appropriately. So as artificial intelligence continues to progress, we see ones that are trying to understand, well, what makes people happy? How would they increase our happiness? How would they keep themselves from breaking down if something's broken inside? They have that self-awareness to be able to fix it. And just based on all that information, predicting which action would work the best, what would help people. If I know that you're having a cup of coffee first thing in the morning is what makes you happy as a robot, I might make you a cup of coffee every morning at the same time to help your life and help you grow. That'd be the self-awareness, is being able to know all those different things. Types of machine learning, and like I said on the last slide, this is very important. This is very important. If you decide to go in and get certified in machine learning or know more about it, these are the three primary types of machine learning. The first one is supervised learning. Systems are able to predict future outcome based on past data. Requires both an input and an output to be given to the model for it to be trained. So in this case, we're looking at anything where you have 100 images of a bicycle, and those 100 images are bicycle. So they're preset. Someone already looked at all 100 images and said, these are pictures of bicycles. And so the computer learns from those, and then it's given another picture, and maybe the next picture is a bicycle, and it says, oh, that resembles all these other bicycles, so it's a bicycle. And the next one's a car, and it says, it's not a bicycle. That would be supervised learning, because we had to train it. We had to supervise it. Unsupervised learning. Systems are able to identify hidden patterns from the input data provided by making the data more readable and organized. The patterns, similarities, or anomalies become more evident. You'll heard the term cluster. How do you cluster things together? Some of these things go together, some of these don't. This is unsupervised, where it can look at an image and start pulling the different pieces of the image out because they aren't the same. All the parts of the human are not the same as a fuzzy tree behind them because it's slightly out of focus, which is not the same as the beach ball. It's unsupervised because we never told it what a beach ball was, we never told it what the human was, and we never told it that those were trees. All we told it was, hey, separate this picture by things that don't match and things that do match and come together. And finally, there's reinforcement learning. Systems are given no training. It learns on the basis of the reward punishment it received for performing its last action. It helps increase the efficiency of a tool function or a program. Reinforced learning, or reinforcement learning, is kind of, you give it a yes or no. Yes, you gave me the right response. No, you didn't. And then it looks at that and says, oh, okay, so based on this data coming in, what I gave you was a wrong response, so next time I'll give you a different one. Comparing machine learning and deep learning. So remember that deep learning is a subcategory of machine learning. So it's one of the many tools. And so we're grouping a ton of machine learning tools all together. Linear regression, k-means clustering. There's all kinds of cool tools out there you can use in machine learning. Enables machines to make decisions on their own based on past data. Enables machines to make decisions with the help of artificial neural networks. So it's doing the same thing, but we're using an artificial neural network as opposed to one of the more traditional machine learning tools. Needs only a small amount of training data. This is very important. When you're talking about machine learning, they're usually not talking about huge amounts of data. We're talking about maybe your spreadsheet from your business and your totals for the end of the year. When you're talking about neural networks, you usually need a large amount of data to train the data. So there's a lot of training involved. If you have under 500 points of data, that's probably not going to go into machine learning. Or maybe you have, like the case of one of the things, 500 points of data and 30 different fields. It starts getting really confusing there in artificial intelligence or machine learning, and the deep learning aspect really shines when you get to that larger data that's really complex. Works well on a low-end systems. So a lot of the machine learning tools out there you can run on your laptop with no problem and do the calculations there. Where with the machine learning, you usually needs a higher end system to work. It takes a lot more processing power to build those neural networks and to train them. It goes through a lot of data. We're talking about the general machine learning tools. Most features need to be identified in advance and manually coded. So there's a lot of human work on here. The machine learns the features from the data it is provided. So again, it's like a magic box. You don't have to know what a tire is. It figures it out for you. The problem is divided into parts and solved individually and then combined. So in machine learning, you usually have all these different tools and use different tools for different parts. And the problem is solved in an end-to-end manner. So you only have one neural network or two neural networks that is bringing the data in and putting it out. It's not going through a lot of different processes to get there. And remember, you can put machine learning and deep learning together. So you don't always have just the deep learning solving the problem. You might have it solving one piece of the puzzle. With regular machine learning and most machine learning tools out there, they take longer to test and understand how they work. And with the deep learning, it's pretty quick. Once you build that neural network, you test it and you know. So we're dealing with very crisp rules, limited resources. You have to really explain how the decision was made when you use most machine learning tools. But when you use the deep learning tool inside the machine learning tools, the system takes care of it based on its own logic and reasoning. And again, it's like a magic black box. You really don't know how it came up with the answer. You just know it came up with the right answer. A glimpse into the future. So a quick glimpse into the future, artificial intelligence, be using it to detecting crimes before they happen, humanoid AI helpers, which we already have a lot of. There'll be more and more. Maybe it'll actually be androids. That'd be cool to have an android that comes and gets stuff out of my fridge for me. Machine learning, increasing efficiency in healthcare. That's really big in all the forms of machine learning. Better marketing techniques. Any of these things, if we get into the sciences, it's just off the scale. Machine learning and artificial intelligence go everywhere. And then the subcategory deep learning, increased personalization. So what's really nice about the deep learning is it's going to start now catering to you. That'll be one of the things we see more and more of. And we'll have more of a hyper-intelligent personal assistant. I'm excited about that.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
Now let's look into the types of machine learning. Machine learning is primarily of three types. First one is supervised machine learning. As the name suggests, you have to supervise your machine learning while you train it to work on its own. It requires labeled training data. Next up is unsupervised learning, wherein there will be training data but it won't be labeled. Finally, there's reinforcement learning, wherein the system learns on its own. Let's talk about all these types in detail. Let's try to understand how supervised learning works. Look at the pictures very carefully. The monitor depicts the model or the system that we are going to train. This is how the training is done. We provide a data set that contains pictures of a kind of a fruit, say an apple. Then, we provide another data set which lets the model know that these pictures were that of a fruit called apple. This ends the training phase. Now, what we will do is we provide a new set of data which only contains pictures of apple. Now here comes the fun part. The system can actually tell you what fruit it is. And it will remember this and apply this knowledge in future as well. That's how supervised learning works. You are training the model to do a certain kind of an operation on its own. This kind of a model is generally used into filtering spam mails from your email accounts as well. Yes, surprised, aren't you? So let's move on to unsupervised learning now. Let's say we have a data set which is cluttered. In this case, we have a collection of pictures of different fruits. We feed this data to the model and the model analyzes the data to figure out patterns in it. In the end, it categorizes the photos into three types, as you can see in the image, based on their similarities. So, you provide the data to the system and let the system do the rest of the work. Simple, isn't it? This kind of a model is used by Flipkart to figure out the products that are well suited for you. Honestly speaking, this is my favorite type of machine learning out of all the three. And this type has been widely shown in most of the sci-fi movies lately. Let's find out how it works. Imagine a newborn baby. You put a burning candle in front of the baby. The baby does not know that if it touches the flame, its fingers might get burned. So it does that anyway and gets hurt. The next time you put that candle in front of the baby, it will remember what happened the last time and would not repeat what it did. That's exactly how reinforcement learning works. We provide the machine with a data set wherein we ask it to identify a particular kind of a fruit, in this case an apple. So what it does as a response, it tells us that it's a mango. But as we all know, it's a completely wrong answer. So as a feedback, we tell the system that it's wrong, it's not a mango, it's an apple. What it does, it learns from the feedback and keeps that in mind. When the next time, when we ask a same question, it gives us the right answer. It is able to tell us that it's actually an apple. That is a reinforced response. So that's how reinforcement learning works. It learns from its mistakes and experiences. This model is used in games like Prince of Persia or Assassin's Creed or FIFA, wherein the level of difficulty increases as you get better with the games. Just to make it more clear for you, let's look at a comparison between supervised and unsupervised learning. Firstly, the data involved in case of supervised learning is labeled. As we mentioned in the examples previously, we provide the system with a photo of an apple and let the system know that this is actually an apple. That is called labeled data. So the system learns from the labeled data and makes future predictions. Now, unsupervised learning does not require any kind of labeled data because its work is to look for patterns in the input data and organize it. The next point is that you get a feedback in case of supervised learning. That is, once you get the output, the system tends to remember that and uses it for the next operation. That does not happen for unsupervised learning. And the last point is that supervised learning is mostly used to predict data, whereas unsupervised learning is used to find out hidden patterns or structures in data. I think this would have made a lot of things clear for you regarding supervised and unsupervised learning.
Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, and then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So when we talk about types of data, we have in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range if you have 10,000 to 20,000. Number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true-false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative, numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete will be could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's what we're talking about, a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart, or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary, this is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have 2 variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. They kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had a reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, small case a for the top row. Or, I mean, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix. And then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now again, you're counting matrices. You want to check your dimensions of the matrix. The shape. You'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at 2 variable. So this is a 2 variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of 2 matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time, where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigenvectors vectors and eigenvalues. values. Eigenvectors, vectors, the vectors that don't change their span while transformation, and eigenvalues, values, the scalar values that are associated to the vectors. conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigene vector. 2 is the eigene value. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigene value. And you can see here, vector after line transition, we have 3A. A is the eigene vector. 3 is the eigene value. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigene values. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook. And we'll create a new notebook called Linear Algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create 2 different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our 2 arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as A plus B, I can also do A plus B dot T, and you're going to see that that will come out the same, the 30, 24, whether I transpose A and B or transpose them both at the end. And likewise, we can very easily subtract 2 vectors. I can go A minus B, and we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. And what we're talking about here is I have this array here, U, and if I go A times U, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a 2-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is well, let's walk through it. We'll go ahead and start by defining 2 NumPy arrays. We'll have 10, 20, 25, 6, or our U and our V. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of u comma v. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is of course 10, 10 minus 8 is 2, 4 minus 46 is minus 42, and so forth. So same as a subtraction as before, we just call it matrix subtraction. It's identical. Now if you remember up here we had scalar addition where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices that you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1 depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then of course it equals the dot, A inverse of A, with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go ahead and have here's our array. We'll go ahead and run this, and you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably really is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, I mean, if you ever took a basic calculus class, they would draw bars down here and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. It looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, the differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from c to d and a to b of f of x of y dx dy equals the sum of a to b, sum of c to d of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals a change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? You know, speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I mean, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick. Gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. we're just saying if it's if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits in built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught. There's your start value. So your function, your start value, there's all kinds of things that come in here that you can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. What this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does that come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you gotta be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call our expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say, this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So we talk about the mean. It is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was $1,24000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is, and then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have, like, if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools, as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, whoops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000, so the halfway mark is significantly below the average. Why? Because we have somebody in here who makes 189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample. And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000, so half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what your your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode. Although the standard one's pretty good. We can of course do the range. which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which would just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and like just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically. But just in case, I always put it in there. Import matplot library, pyplot as PLT. That's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our, in this case we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AXV line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But, picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture, movie ratings and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about a hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who were given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people, Nick, Rob, Imlia, and Summer. Now Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e. whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e. his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states Whenever something is happening, a new theory is preferred instead of an old one. And so the two hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these two have zero relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is a probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value, it is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct, there is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 2-300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%. You have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. So, there's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this is one of the cases, is rolling 2 dice and gambling. There's also binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means that each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1, so that accounts for 100% of the game. Probability for getting K wins in N matches is calculated, and we're talking like, so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's the percentage on those? And the probability for getting K wins in N matches is calculated by Px equals K equals NCK P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers, and we end up with a 0.0009765,625. So a very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the P equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology, location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, If you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between one standard deviation. Around 95% of the results are found between two standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's that kind of funky U. It just means the mean. And then the sigma is the standard deviation. And that's the O with the little arrow off to the right, or the little waggly tail going up. The O with the line on it. So mu minus 2 sigma is your 95% of the results are found between two standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if we're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula. And it's really, it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math. But it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but you know, it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A. Prior probability of 10% people having lung disease. And then probability B. Probability that a patient smokes is 15%. And the probability of B, if B, then A. The probability of a patient smokes even though they have lung disease is 5%. And probability of A is B. Probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back-end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in? Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. You can remember we had a slide on this earlier, where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces, repeat equals in dice. And we'll go ahead and just run this. And you can see here, it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence, and as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something. Let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y, remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome, so we can see what that looks like. There we go. And of course, I did forget to add the print in the middle because we're looping through and putting an end on the setup on there. So we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability, last line, so we can just type it in, we end up with a 0.3333 chance. And it's roughly a third. And we might want to make this look nice, so let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255 or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. I mean, a false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you know, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take, and there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this true that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
So without much further ado, let's get started. So deep learning is considered to be a part of machine learning. So this diagram very nicely depicts what deep learning is. At a very high level, you have the all-encompassing artificial intelligence, which is more a concept rather than a technology or a technical concept, right? So it is more of a concept at a very high level, artificial intelligence. Under the hood, word is actually machine learning and deep learning. And machine learning is a broader concept, you can say, or a broader technology, and deep learning is a subset of machine learning. The primary difference between machine learning and deep learning is that deep learning uses neural networks and it is suitable for handling large amounts of unstructured data. And the last but not least, one of the major differences between machine learning and deep learning is that in machine learning, the feature extraction or the feature engineering is done by the data scientists manually. But in deep learning, since we use neural networks, the feature engineering happens automatically. So that's a little bit of a quick difference between machine learning and deep learning. And this diagram very nicely depicts the relation between artificial intelligence, machine learning, and deep learning. Now, why do we need deep learning? Machine learning was there for quite some time and it can do a lot of stuff that probably what deep learning can do, but it's not very good at handling large amounts of unstructured data like images, voice, or even text for that matter. So traditional machine learning is not that very good at doing this. Traditional machine learning can handle large amounts of structured data, but when it comes to unstructured data, it's a big challenge. So that is one of the key differentiators for deep learning. So that is number one. And increasingly for artificial intelligence, we need image recognition and we need to process, analyze images and voice. That's the reason deep learning is required compared to, let's say, traditional machine learning. It can also perform complex algorithms, more complex than, let's say, what machine learning can do. And it can achieve best performance with the large amounts of data. So the more you have the data, let's say reference data or labeled data, the better the system will do because the training process will be that much better. And last but not least, with deep learning, you can really avoid the manual process of feature extraction. Those are some of the reasons why we need deep learning. Some of the applications of deep learning. Deep learning has made major inroads and it is a major area in which deep learning is applied is healthcare. And within healthcare, particularly oncology, which is basically cancer related stuff. One of the issues with cancer is that a lot of cancers today are curable. They can be cured. They are detected early on. And the challenge with that is when a diagnostics is performed, let's say an image has been taken of a patient, to detect whether there is cancer or not, you need a specialist to look at the image and determine whether the patient is fine or there is any onset of cancer. And the number of specialists are limited. So if we use deep learning, if we use automation here, or if we use artificial intelligence here, then the system can, with a certain amount of the good amount of accuracy, determine whether a particular patient is having cancer or not. So the prediction or the detection process of a disease like cancer can be expedited. The detection process can be expedited, can be faster without really waiting for a specialist. We can obviously then, once the artificial intelligence detects or predicts that there is an onset of a cancer, this can be cross-checked by a doctor. But at least the initial screening process can be automated, and that is where the current focus is with respect to deep learning in healthcare. What else? Robotics is another area. Deep learning is majorly used in robotics, and you must have seen nowadays robots are everywhere, humanoids, the industrial robots which are used for manufacturing process. You must have heard about Sophia, who got citizenship with Saudi Arabia, and so on. There are multiple such robots which are knowledge oriented, but there are also industrial robots that are used in industries, in the manufacturing process, and increasingly in security and also in defense. For example, image processing. Video is fed to them and they need to be able to detect objects, obstacles, and so on and so forth. So that's where deep learning is used. They need to be able to hear and make sense of the sounds that they are hearing. That needs deep learning as well. So robotics is a major area where deep learning is applied. Then we have self-driving cars or autonomous cars. You must have heard of Google's autonomous car, which has been tested for millions of miles and pretty much incident-free. There were, of course, a couple of incidents here and there, but it is considered to be fairly safe. And there are today a lot of automotive companies. In fact, pretty much every automotive company worth its name is investing in self-driving cars or autonomous cars. And it is predicted that in the next probably 10 to 15 years, these will be in production and they will be used extensively in real life. Right now, they are all in R&D and in test phases, but pretty soon these will be on the road. So this is another area where deep learning is used. And how is it used? Where is it used? Within autonomous driving, the car actually is fed with video of surroundings, and it is supposed to process that information, process that video, and determine if there are any obstacles. It has to determine if there are any cars in the side. It will detect whether it is driving in the lane. Also, it has to determine whether the signal is green or red, so that accordingly it can move forward or wait. So for all these video analysis, deep learning is used. In addition to that, the training, overall training to drive the car happens in a deep learning environment. So again, a lot of scope here to use deep learning. A couple of other applications are machine translation. So today we have a lot of information, and very often this information is in one particular language, and more specifically in English. And people need information in various parts of the world. It is pretty difficult for human beings to translate each and every piece of information or every document into all possible languages. There are probably at least hundreds of languages, or if not more. To translate each and every document into every language is pretty difficult. Therefore, we can use deep learning to do pretty much like a real-time translation mechanism. So we don't have to translate everything and keep it ready, but we train applications or artificial intelligence systems that will do the translation on the fly. For example, you go to somewhere like China and you want to know what is written on a signboard. Now, it is impossible for somebody to translate that and put it on the web or something like that. So you have an application which is trained to translate stuff on the fly. So this can be running on your mobile phone, on your smartphone. You scan this, the application will instantly translate that from Chinese to English. That is one. Then there could be web applications where there may be a research document which is all in maybe Chinese or Japanese, and you want to translate that to study that document, or in that case you need to translate that. So therefore, deep learning is used in such situations as well, and that is again on demand. So it is not like you have to translate all these documents from other languages into English in one shot and keep it somewhere. That is again pretty much an impossible task, but on a need basis. So you have systems that are trained to translate on the fly. So machine translation is another major area where deep learning is used. Then there are a few other upcoming areas where synthesizing is done by neural nets. For example, music composition and generation of music. So you can train a neural net to produce music, even to compose music. So this is a fun thing. This is still upcoming. It needs a lot of effort to train such neural net. It has been proved that it is possible. So this is a relatively new area. And on the same lines, colorization of images. So these two images on the left hand side is a grayscale image or a black and white image. This was colored by a neural net or a deep learning application. As you can see, it's done a very good job of applying the colors, and obviously this was trained to do this colorization. But yes, this is one more application of deep learning. What are the different types of machine learning algorithms? Machine learning algorithms are broadly classified into three types: the supervised learning, the unsupervised learning, and reinforcement learning. Supervised learning in turn consists of techniques like regression and classification, and unsupervised learning, we use techniques like association and clustering. And reinforcement learning is a recently developed technique, and it is very popular in gaming. Some of you must have heard about AlphaGo. So this was developed using reinforcement learning. Primary difference between supervised learning and unsupervised learning. Supervised learning is used when we have historical data and we have labeled data, which means that we know how the data is classified. So we know the classes if we are doing classification, or we know the values when we are doing regression. So if we have historical data with these values, which are known as labels, then we use supervised learning. In case of unsupervised learning, we do not have past labeled data, historical labeled data. So we use techniques like association and clustering to maybe form clusters or new classes maybe, and then we move from there. In case of reinforcement learning, the system learns pretty much from scratch. There is an agent and there is an environment. The agent is given a certain target and it is rewarded when it is moving towards that target, and it is penalized if it is moving in a direction which is not achieving that target. So it's more like a carrot and stick model. So what is the difference between these three types of algorithms? Supervised algorithms or supervised learning algorithms are used when you have a specific target value that you would like to predict. The target could be categorical, having two or more possible outcomes or classes, if you will. That is what is classification. Or the target could be a value which can be measured. And that's where we use regression. Like for example, weather forecasting, you want to find the temperature. Whereas in classification, you want to find out whether this is a fraud or not a fraud, or if it is email spam, whether it is spam or not spam. So that is a classification example. So if you know, or this is known as labeled information, if you have the labeled information, then you use supervised learning. In case of unsupervised learning, we have input data, but we don't have the labels or what the output is supposed to be. So that is when we use unsupervised learning techniques like clustering and association, and we try to analyze the data. In case of reinforcement learning, it allows the agent to automatically determine the ideal behavior within a specific context, and it has to do this to maximize the performance. Like for example, playing a game. So the agent is told that you need to score the maximum score possible without losing lives. So that is a target that is given to the agent, and it is allowed to learn from scratch, play the game itself multiple times, and slowly it will learn the behavior which will increase the score and keep the lives to the maximum. That's an example of reinforcement learning.
When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far, where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there, like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally, we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half you can see where we've broken that down into pieces, and as it goes through the first 2 points it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y where the sum equals 66. This all comes from our formula for calculating a straight line where y equals the slope times x plus the coefficient c. So we go down below and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part if you read through the brackets you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66, and take all that and you subtract it from the sum of x times the sum of y, and those have both been computed. So you have 15 times 20. And on the bottom we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1 all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row. That's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the Pandas. You could also open this up in an Excel and it would separate it, since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is Pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any two of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one-hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit,
In this case, we do X train and Y train because we're using the training data, X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy X equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x test. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have y_predict equals regressor.predict x test going in, and this gives us y_predict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103,009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the R² value, that's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R² value. We're looking at the error. So, in the R2 score, we take our Y test versus our Y predict. Y test is the actual values we're testing. That was the one that was given to us so we know are true. The Y predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R² value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. So now that we have a successful linear regression model.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the X and Y axis. X is the number of years since the last service was performed, and Y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along X and Y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion, that is a no, and this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between, and what is the employee's rating, okay? And ratings can be continuous, that is not an issue. But the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because it looks like there will be a lot of errors. The root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images, that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times, and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right? This is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose, we use the fit method. There is a method called fit, which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
There's all kinds of regression models that come out of this. So we put them side by side. We have our linear regression, which is a predictive number used to predict a dependent output variable based on independent input variable. Accuracy is measured using least squares estimation. So that's where you take, you could also use absolute value. The least squares is more popular. There's reasons for that mathematically and also for computer runtime. But it does give you an accuracy based on the least square estimation. The best fit line is a straight line, and clearly that's not always used in all the regression models. There's a lot of variations on that. The output is a predicted integer value. Again, this is what we're talking about when we talk about linear regression. And we're talking about regression, it means the numbers coming out. Linear usually means we're looking for that line versus a different model. And it's used in business domain, forecasting stocks. It's used as a basis of most predictions with numbers. So if you're looking at a lot of numbers, you're probably looking at a linear regression model. For instance, if you do just the high lows of the stock exchange, and you're going to take a lot more of that if you want to make money off the stock, you'll find that the linear regression model fits probably better than almost any of the other models, even high-end neural networks and all these other different machine learning and AI models, because they're numbers. They're just a straight set of numbers. You have a high value, a low value, volume, that kind of thing. So when you're looking at something that's straight numbers and are connected in that way, usually you're talking about a linear regression model, and that's where you want to start. A logistic regression model used to classify dependent output variable based on independent input variable. So just like the linear regression model and like all of our machine learning tools, you have your features coming in. And so in this case you might have label, an image or something like that is probably the very popular thing right now, labeling broccoli and vegetables or whatever. Accuracy is measured using maximum likelihood estimation. The best fit is given by a curve. And we saw that when we're talking about linear regression, you definitely are talking about a straight line, although there is other regression models that don't use straight lines. And usually when you're looking at a logistic regression, the math, as you saw, was still kind of a Euclidean line, but it's now got that sigmoid activation, which turns it into a heavily weighted curve. And the output is a binary value between 0 and 1. And it's used for classification. Image processing, as I mentioned, is what people usually think of, although they use it for classification of like a window of things. So you could take a window of stock history and you could generate classifications based on that and separate the data that way. If it's going to be that this particular pattern occurs, it's going to be upward trending or downward trending. In fact, a number of stock traders use that not to tell them how much to bid or what to bid, but they use it as to whether it's worth looking at the stock or not, whether the stock's going to go down or go up. And it's just a 0 or 1. Do I care or do I even want to look at it? So let's do a demo so you can get a picture of what this looks like in Python code. Let's predict the price at which insurance should be sold to a particular customer based on their medical history. We will also classify on a mushroom dataset to find the poisonous and non-poisonous mushrooms. And when you look at these two datas, the first one, we're looking at the price. So the price is a number. So let's predict the price which the insurance should be sold to. And the second one is we're looking at either it's poisonous or it's not poisonous. So first off, before we begin the demo, I'm in the Anaconda Navigator. In this one, I've loaded the Python 3.6 and using the Jupyter Notebook. And you can use Jupyter Notebook by itself. You can use the Jupyter Lab, which allows multiple tabs. It's basically the notebook with tabs on it. But the Jupyter Notebook is just fine, and it'll go into Google Chrome, which is what I'm using for my Internet Explorer. And from here we open up new and you'll see Python 3, and again this is loaded with Python 3.6. And we're doing the linear versus logic regression, or logit. You'll see L-O-G-I-T is one of the names that kind of pops up when you do a search on here. But it is a logic. We're looking at the logistic regression models. And we'll start with the linear regression because it's easy to understand. You draw a line through stuff. And so in programming, we got a lot of stuff to unfold here in our startup as we preload all of our different parts. And let's go ahead and break this up. We have at the beginning import pandas. So this is our data frame. It's just a way of storing the data. Think of when you talk about a data frame, think of a spreadsheet. You have rows and columns. It's a nice way of viewing the data. And then we have, we're going to be bringing in our pre-processing label encoder. I'll show you what that is. When we get down to it, it's easier to see in the data, but there's some data in here like sex. It's male or female, so it's not like an actual number. It's either you're one or the other. That kind of stuff ends up being encoded. That's what this label encoder is right here. We have our test split model. If you're going to build a model, you do not want to use all the data. You want to use some of the data and then test it to see how good it is. And if it can't have seen the data you're testing on until you're ready to test it on there and see how good it is. And then we have our logistic regression model, our categorical one, and then we have our linear regression model. These are the two, these right here. Let me just clear all that. There we go. These two right here are what this is all about. Logistic versus linear. Is it categorical? Are we looking for a true false, or are we looking for a specific number? And then finally, usually at the very end, we have to take and just ask how accurate is our model. Did it work? If you're trying to predict something, in this case we're going to be doing insurance costs. How close to the insurance cost does it measure that we expect it to be? You know, if you're an insurance company, you don't want to promise to pay everybody's medical bill and not be able to. And in the case of the mushrooms, you probably want to know just how much at risk you are for following this model as to far as whether you're going to eat a poisonous mushroom and die or not. So we'll look at both of those, and we'll talk a little bit more about the shortcomings and the value of these different processes. So let's go ahead and run this. This is loaded the data set on here, and then because we're in Jupyter Notebook, I don't have to put the print on there. We just do data set, and it prints out all the different data on here, and you can see here for our insurance, because that's what we're starting with. We're loading that with our pandas, and it prints it in a nice format where you can see the age, sex, body mass index, number of children, smoker. So this might be something that the insurance company gets from the doctor. It says, hey, this is what we need to know to give you a quote for what we're going to charge you for your insurance. And you can see that it has 1,338 rows and 7 columns. You can count the columns, 1, 2, 3, 4, 5, 6, 7. So there's 7 columns on here. And the column we're really interested in is charges. I want to know what the charges are going to be. What can I expect? Not a very good arrow drawn. What to expect them to charge on there. So is this going to be, is this person going to cost me $16,884, or is this person only going to cost me $3,866? How do we guess that so that we can guess what the minimal charge is for their insurance? And then there's one other thing you really need to notice on this data. And I mentioned it before, but I'm going to mention it again because pre-processing data is so much of the work in data science. Sex. Well, how do you deal with female versus male? Are you a smoker? Yes or no? What does that mean? Region. How do you look at region? It's not a number. How do you draw a line between southwest and northwest? They're objects. It's either your southwest or your northwest. It's not like I'm southwest. I guess you could do longitude and latitude, but the data doesn't come in like that. It comes in as true, false, or whatever. It's either your southwest or your northwest. So we need to do a little bit of pre-processing of the data on here to make this work. Oops, there we go. Okay, so let's take a look and see what we're doing with pre-processing. And again, this is really where you spend a lot of time with data science, is trying to understand how and why you need to do that. And so we're going to do, you'll see right up here, label. And then we're going to do a label encoder, one of the modules we brought in. So this is sklearn's label encoder. I like the fact that it's all pretty much automated, but if you're doing a lot of work with the label encoder, you should start to understand how that fits. And then we have label.fit right here, where we're going to go ahead and do the dataset .sex.drop duplicates, and then for dataset sex, we're going to do the label transform the dataset sex. And so we're looking right here at male or female. And so it usually just converts it to a 0 or 1 because there's only 2 choices on here. Same thing with the smoker. It's 0 or 1, so we're going to change the smoker 0 or 1 on this. And then finally we did region down here. Region does it a little bit different. We'll take a look at that. And I think in this case it's probably going to do it because we did it on this label transform. With this particular setup, it gives each region a number, like 0, 1, 2, 3. So let's go ahead and take a look and see what that looks like. Go and run this, and you can see that our new data set has age, that's still a number, sex is 0 or 1, so 0 is female, 1 is male. Number of children, we left that alone. Smoker, 1 or 0, it says no or yes on there. We actually just do 1 for no, 0 or no. Yeah, 1 for no. I'm not sure how it organized them, but it turns the smoker into 0 or 1, yes or no. And then region, it did this as 0, 1, 2, 3, so it's 3 regions. Now, a lot of times when you're working with data science and you're dealing with regions or even word analysis, instead of doing one column and labeling it 0, 1, 2, 3, a lot of times you increase your features, and so you would have region northwest would be 1 column, yes or no. Region southwest would be 1 column, yes or no, true 0, 1. But for this particular setup, this will work just fine on here. Now that we spent all that time getting it set up, here's the fun part. Here's the part where we're actually using our setup on this, and you'll see right here we have our y-linear regression dataset drop the charges, because that's what we want to predict. And so our X linear data set drop the charges, because that's what we're going to predict. We're predicting charges right here, so we don't want that as our input for our features. And our Y output is charges. That's what we want to guess. We want to guess what the charges are. And then what we talked about earlier is we don't want to do all the data at once, so we're going to take 0.3, means 30%. We're going to take 30% of our data, and it's going to be as the testing site. So here's our Y test and our X test down there. And so that part, our model will never see it until we're ready to test to see how good it is. And then of course right here you'll see our training set, and this is what we're going to train it. We're going to train it on 70% of the data. And then finally the big ones, this is where all the magic happens. This is where we're going to create our magic setup, and that is right here. Our linear model, we're going to set it equal to the linear regression model, and then we're going to fit the data on here. And then at this point, I always like to pull up, if you're working with a new model, it's good to see where it comes from. And this comes from the scikit-learn, and this is the sklearn linear model, linear regression that we imported earlier. And you can see they have different parameters. The basic parameter works great if you're dealing with just numbers. I mentioned that earlier with stock, high-lows. This model will do as good as any other model out there if you're doing just the very basic high-lows and looking for a linear fit, a regression model fit. And one of the things when I'm looking at this is I look for methods. And you'll see here's our fit that we're using right now, and here's our predict. And we'll actually do a little bit in the middle here as far as looking at some of the parameters hidden behind it, the math that we talked about earlier. And so when we go in this, and we go ahead and run this, you'll see it loads the linear regression model and just has a nice output that says, hey, I loaded the linear regression model. And then the second part is we did the fit. And so this model is now trained. Our linear model is now trained on the training data. And so one of the things we can look at is the, for IDX and column name and enumerate X linear trained columns. Kind of an interesting thing. This prints out the coefficients. So when you're looking at the back end of the data, you remember we had that formula, bxx1 plus bxx2 plus the intercept, and so forth. These are the actual coefficients that are in here. This is what it's actually multiplying these numbers by. And you can see like region gets a minus value, so when it adds it up, I guess region. You can read a lot into these numbers. It gets very complicated. There's ways to mess with them. If you're doing a basic linear regression model, you usually don't look at them too closely. But you might start looking in these and saying, hey, you know what, smoker, look how smoker impacts the cost. It's just massive. So this is a flag that, hey, the value of the smoker really affects this model. And then you can see here where the body mass index, so somebody who is overweight is probably less healthy and more likely to have cost money. And then of course age is a factor, and then you can see down here we have sex is then a factor also, and it changes as you go in there. Negative number, it probably has its own meaning on there. Again, it gets really complicated when you dig into the workings and how the linear model works on that. And so we can also look at the intercept. This is just kind of fun. So it starts at this negative number and then adds all these numbers to it. That's all that means. That's our intercept on there. And that fits the data we have on that. And so you can see right here, we can go back and, oops, give me just a second. There we go. We can go ahead and predict the unknown data, and we can print that out. And if you're going to create a model to predict something, we'll go ahead and predict it. Here's our Y prediction value, linear model predict. And then we'll go ahead and create a new data frame. In this case from our X linear test group. We'll go ahead and put the cost back into this data frame. And then the predicted cost, we're going to make that equal to our Y prediction. And so when we pull this up, you can see here that we have the actual cost and what we predicted the cost is going to be. There's a lot of ways to measure the accuracy on there, but we're going to go ahead and jump into our mushroom data. And so in this, you can see here we've run our basic model. We've built our coefficients. You can see the intercept, the back end. You can see how we're generating a number here. Now with mushrooms, we want a yes or no. We want to know whether we can eat them or not. And so here's our mushroom file. We're going to go ahead and run this, take a look at the data. And again, you can ask for a copy of this file. Send a note over to Simplilearn.com. And you can see here that we have a class, the cap shape, cap surface, and so forth. So there's a lot of feature. In fact, there's 23 different columns in here going across. And when you look at this, I'm not even sure what these particular like PEE, PE. I don't even know what the class is on this. I'm going to guess by the notes that the class is poisonous or edible. So if you remember before, we had to do a little pre-coding on our data. Same thing with here. We have our cap shape, which is B or X or K. We have cap color. These really aren't numbers, so it's really hard to do anything with just a single number. So we need to go ahead and turn those into a label encoder, which again, there's a lot of different encoders. With this particular label encoder, it's just switching it to 0, 1, 2, 3 and giving it an integer value. In fact, if you look at all the columns, all of our columns are labels. And so we're just going to go ahead and loop through all the columns in the data, and we're going to transform it into a label encoder. And so when we run this, you can see how this gets shifted from XBXXK to 0, 1, 2, 3, 4, 5, or whatever it is. Class is 0, 1, 1 being poisonous, 0 looks like it's editable, and so forth on here. So we're just encoding it. If you were doing this project, depending on the results, you might encode it differently. Like I mentioned earlier, you might actually increase the number of features as opposed to labeling it 0, 1, 2, 3, 4, 5. In this particular example, it's not going to make that big of a difference how we encode it. And then, of course, we're looking for the class, whether it's poisonous or edible. So we're going to drop the class in our X logistics model, and we're going to create our Y logistics model is based on that class. So here's our XY. And just like we did before, we're going to go ahead and split it using 30% for test, 70% to program the model on here. And that's right here. Whoops, there we go. There's our train and test. And then you'll see here on this next setup, this is where we create our model. All the magic happens right here. We go ahead and create a logistics model. I've upped the max iterations. If you don't change this for this particular problem, you'll get a warning that says this has not converged. Because that's what it does, is it goes through the math and it goes, hey, can we minimize the error? And it keeps finding a lower and lower error, and it still is changing that number. So that means it hasn't converged yet. It hasn't found the lowest amount of error it can. And the default is 100. There's a lot of settings in here. So when we go in here to, let me pull that up from the sklearn. So we pull that up from the sklearn model. You can see here we have our logistic. It has our different settings on here that you can mess with. Most of these work pretty solid on this particular setup, so you don't usually mess a lot. Usually I find myself adjusting the iteration, and I'll get that warning and then increase the iteration on there. And just like the other model, you can go, just like you did with the other model, we can scroll down here and look for our methods. And you can see there's a lot of methods available on here. And certainly there's a lot of different things you can do with it. But the most basic thing we do is we fit our model, make sure it's set right, and then we actually predict something with it. So those are the two main things we're going to be looking at on this model, is fitting and predicting. There's a lot of cool things you can do that are more advanced, but for the most part, these are the two which I use when I'm going into one of these models and setting them up. So let's go ahead and close out of our sklearn setup on there. And we'll go ahead and run this. And you can see here it's now loaded this up there. We now have a logistic model. And we've gone ahead and done a predict here also, just like I was showing you earlier. So here's where we're actually predicting the data. So we've done our first two lines of code as we create the model. We fit the model to our training data. And then we go ahead and predict for our test data. Now, in the previous model, we didn't dive into the test score. I think I just showed you a graph, and we can go in there, and there's a lot of tools to do this. We're going to look at the model score on this one. And let me just go ahead and run the model score. And it says that it's pretty accurate. We're getting a roughly 95% accuracy. Wow, that's good. 95% accuracy. 95% accuracy might be good for a lot of things. But when you look at something as far as whether you're going to pick a mushroom on the side of the trail and eat it, we might want to look at the confusion matrix. And for that, we're going to put in our Logistic test, the actual values of edible and unedible, and we're going to put in our prediction value. And if you remember on here, let's see, I believe it's poisonous was 1, 0 is edible. So let's go ahead and run that, 0, 1. 0 is good. So here is a confusion matrix, and this is, if you're not familiar with these, we have true, 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 false, true, false, false, false. So it says out of the edible mushrooms, we correctly labeled 1,201 mushrooms edible that were edible. And we correctly measured 1,113 poisonous mushrooms as poisonous. But here's the kicker. I labeled 56 edible mushrooms as being poisonous. Well, that's not too big of a deal. We just don't eat them. But I measured 68 mushrooms as being edible that were poisonous. So probably not the best choice to use this model to predict whether you're going to eat a mushroom or not. And you'd want to dig a little deeper before you start picking mushrooms off the side of the trail. So a little warning there, when you're looking at any of these data models, looking at the error and how that error fits in with what domain you're in, domain in this case being edible mushrooms, be a little careful. Make sure that you're looking at them correctly. So we've looked at edible or not edible. We've looked at regression model as far as the end values, what's going to be the cost and what our predicted cost is, so we can start figuring out how much to charge these people for their insurance. And so these really are the fundamentals of data science. When you pull them together, when I say data science, I'm talking about your machine learning code. And hopefully you got a little bit out of here. Again, you can contact our Simplilearn team and get a copy of these files or get more information on this.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
A confusion matrix represents a table layout of the different outcomes of prediction and results of a classification problem and helps visualize its outcomes. And so you see here we have our simple chart, predicted and actual. The confusion matrix helps us identify the correct predictions of a model for different individual classes, as well as the errors. So you'll see here that the values predicted by our classifier are along the rows. This is what we're going to guess it is, or our model is guessing what this is based on its training. So we've already trained the model to guess whether it's spam or not spam or whatever it is you're working on. And then the actual values of our data set are along the columns. So this is the actual value it's supposed to be. People who can speak English will be classified as positives. So, because they have remember 0 or 1. Do you speak English? Yes, no. And you could extend this that they might have, do you speak French? Do you speak whatever languages? And so you might have a whole lot of classifiers that you would look at each one of these. People who cannot speak English will be classified as negatives. So there'll be a 0. So, 0 ones. The number of times our actual positive values are equal to predicted positive values gives us true positive, TP. The number of times our actual negative values are equal to predictive negative values gives us true negative, TN. The number of times our model wrongly predicts negative values as positives gives us a false positive, FP. And you'll see when you're working with these a lot, memorizing that it's false positive, you can easily figure out what that is, and pretty soon you're just looking at the FP or the TP, depending on what you're working on. And the number of times our model wrongly predicts positive values as negatives gives us a false negative, FP. Now, I'm going to do a quick step out here. Let's say you're working in the medical and we're talking about cancer. Do you really want a bunch of false negatives? You want 0 under false negative. So when we look at this confusion matrix, if you have 5% false positives and 5% false negatives, it'd be much better to even have 20% false positives because they go in and test it, and 0 false negatives. The same might be true if you're working on, say, a car driving. Is this a safe place for the car to go? Well, you really don't want any false positives. Yes, this is safe right over the cliff. So again, when you're working on the project or whatever it is you're working on, this chart suddenly has huge value. We were talking about spam email. How many important emails, say from your banking overdraft charge coming in, that you want to be a true false negative? You don't want it to go in the spam folder. Likewise, you want to get as much of the spam out of there, but you don't want to miss anything really important. Confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics: accuracy, precision, recall, and F1 score. The F1 score is the one I usually hear the most, and accuracy is usually what you put on your chart when you're sending in front of the shareholders. How accurate is it? People understand accuracy. F1 score is a little bit more on the math side, and so you got to be a little careful when you're quoting F1 scores in the when you're sitting there with all the shareholders, because a lot of them will just glaze over. So confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics. Accuracy. The accuracy is used to find the portion of the correctly classified values. It tells us how often our classifier is right. It is the sum of all true values divided by the total values. And this makes sense. Again, it's one of those things. I don't want to, it depends on what you're looking for. Are you looking for not to miss any spam mails? Are you looking to drive down the road and not run anybody over? Precision is used to calculate the model's ability to classify positive values correctly. It answers the question, when the model predicts a positive value, how often is it right? It is the true positive divided by the total number of predicted positive values. Again, this one depends on what project you're working on, whether this is what you're going to be focusing on. So recall, it is used to calculate the model's ability to predict positive values. How often does the model actually predict the correct positive values? It is the true positives divided by the total number of actual positive values. And then your F1 score. It is the harmonic mean of recall and precision. It is useful when you need to take both precision and recall into account. Consider the following 2 confusion matrices, derived from 2 different classifiers. To figure out which one performs better, we can find the confusion matrix for both of them. And you can see we're back to, does it classify whether they can speak English or are non-speaker? They don't know the English language. And so we put these 2 confusion matrices out here. We can go ahead and do the math behind that. We can look up the accuracy. That's the TPN plus TN over the TF plus TN plus FP plus FN. And so we get an accuracy of 0.8125. And we have a precision. If you do the precision, which is your TP, truth positive, over TP plus FP, we get 0.891. And if we do the recall, we'll end up with the 0.825. That's your TP over TP plus FN. And then, of course, your F1 score, which is 2 times precision times recall over precision plus recall. And we get the 0.857. And if we do that with another model, let's say we had 2 different models and we're trying to see which one we want to use for whatever reason, we might go ahead and compute the same things. We have our accuracy, our precision, and our recall, and our F1 score. And as we're looking at this, we might look at the accuracy, because that's really what we're interested in, is how many people are we able to classify as being able to speak English. I really don't want to know I really don't want to know if they're non-speakers. I'd rather miss 10 people speaking English instead of 15. And so you can see from these charts, we probably go with the first model because it does a better job guessing who speaks English and has a higher accuracy, because in this case, that is what we're looking for. So with that, we'll go ahead and pull up a demo so you can see what this looks like in the Python setup and in the actual coding. For this, we'll go into Anaconda Navigator. If you're not familiar with Anaconda, it's a really good tool to use as far as doing display and demos. And for quick development. As a data scientist, I just love the package. Now, if you're going to do something heavier lifting, there's some limitations with Anaconda and with the setup. But in general, you can do just about anything in here with your Python. And for this, we'll go with Jupyter Notebook. Jupyter Lab is the same as Jupyter Notebook. You'll see they now have integration with PyCharm if you work in PyCharm. Certainly there's a lot of other integrations that Anaconda has. And we've opened up my Simplilearn files I work on and create a new file called Confusion Matrix Demo. And the first thing we want to note is the data we're working with. Here I've opened it up in a WordPad or Notepad or whatever. You can see it's got a row of headers, comma separated, and then all the data going down below. And then I save this in the same file so I don't have to remember what path I'm working on. Of course, if you have your data separated and you're working with a lot of data, you probably want to put it into a different folder or file depending on what you're doing. And the first thing we want to do is go ahead and import our tools. We're going to use the pandas. That's our data frame. If you haven't had a chance to work with the data frame, please review Pandas data frame and go into Simplilearn. You can pull up the Pandas data frame tutorial on there. And then we're going to use the Scikit framework, which is all denoted as sklearn. And I can just pull this in. You can see here's the scikit-learn.org with the stable version that you can import into your Python. And from here, we're going to use the train test split. For splitting our data, we're going to do some pre-processing. We're going to use the Logistic regression model. That's our actual machine learning model we're using. And then what this particular setup is about is we're going to do the accuracy score, the confusion matrix, and the classifier report. So let me go ahead and run that and bring all that information in. And just like we opened the file, we need to go ahead and load our data in here. So we're going to go ahead and do our pandas read CSV. And then just because we're in Jupyter Notebook, we can just put data to read the data in here. A lot of times we'll actually, let me just do this. I prefer to do just the head of the data, or the top part. And you can see we have age, sex, I'm not sure what CP stands for, test BPS, cholesterol. So a lot of different measurements. If you were in this domain, you'd want to know what all these different measurements mean. I don't want to focus on that too much because when we're talking about data science, a lot of times you have no idea what the data means. If you've ever looked up the breast cancer measurement, it's just a bunch of measurements and numbers. Unless you're a doctor, you're going to have no idea what those measurements mean. But if it's your specialty in your domain, you better know them. So we're going to go ahead and create y, and we're going to set it equal to the target. So here's our target value here, and it's either 1 or 0. So we have a classifier. If you're dealing with 1, 0, true, false, what do you have? You have a classifier. And then our x is going to be everything except for the target. So we're going to go ahead and drop the target. Axes equals 1. Remember, that's columns versus the index or rows. Axes equals 0 would give you an error, but you would drop like row 2. And then we'll go ahead and just print that out so you can see what we're looking at. And here we have y data, x data, and you can see from the x data we have the x head, and we can go ahead and just do print the y head data and run that. So this is all loading the data that we've done so far. If there's a confusion in there, go back and rewind the tape and review it. And then we need to go ahead and split our data into our xtrain, xtest, ytrain, ytest. And then keep in mind, you always want to split the data before we do the scalar. And the reason is that you want the scalar on the training data to be set on the training data or fit to it, but not on the test data. Think of this as being out in the field. It could actually alter your results. So it's always important to make sure whatever you do to the training data or whatever fit you're doing is always done on the training, not on the test. And then we want to go ahead and scale the data. Now, we are working with linear regression model. And I'll mention this here in a minute when we get to the actual model. So sometimes you don't need to scale it when you're working with linear regression models. It's not going to change your result as much as, say, a neural network where it has a huge impact. But we're going to go ahead and take, here's our X-train, X-test, Y-train, Y-test. We create our scalar. We go ahead and scale. The scale is going to fit the X-train. And then we're going to go ahead and take our X-train and transform it. And then we also need to take our X-test and transform it based on the scale on here, so that our X is now between that nice -1 to 1. And so this is all our pre-data setup. And hopefully all of that looks fairly familiar to you if you've done a number of our other classes and you're up to the setup on here. And then what we want to go ahead and do is create our model. And we're going to use a logistic regression model. And from the logistic regression model, we're going to go ahead and fit our X-train and Y-train, and then we'll run our predicted value on here. And so let's go ahead and run that. And so now we actually have like our X-test and our prediction. So if you remember from our matrix, we're looking for the actual versus the prediction and how those compare. And if I take us back up here, you're going to notice that we imported the accuracy score, the confusion matrix, and the classification report. And there's, of course, our logistic regression, the model we're using for this. And I did mention I was going to talk a little bit about scalar and the regression model. The scalar, on a lot of your regression models, your basic math standard regression models, and I'd have to look it up for the logistic regression model. When you're using a standard regression model, you don't need to scale the data. It's already just built in by the way the model works in most cases. But if you're in a neural network and there's a lot of other different setups, then you really want to take this and fit that on there. And so we can go in and do the accuracy. And this is, if you remember correctly, we were looking at the accuracy with the English speaking. So this is saying our accuracy as to whether this person is, I believe this is the heart data set. It's going to be accurate about 85% of the time as far as whether it's going to predict the person's going to have a heart condition, or the 1 as it comes up with the 0, 1 on there. Which would mean at this point that you have an 85% being correct on telling someone they're extremely high risk for a heart attack kind of thing. And so we want to go ahead and create our confusion matrix. And let me just do that. Of course, the software does everything for us. So we'll go ahead and run this. And you can see right here, here's our 25 prediction, correct predictions right here. And if you remember from our slide, I'll just bring this over so it's a nice visual. We have our true positive, false positive. So we had 25 which were true, that it said, hey, this person's going to be high risk at heart. And we had 4 that were still high risk that it said were false. So out of these 25 people, or out of these 29 people, and that makes sense because you have 0.85, out of 29 people, it was correct on 25 of them. And so here's our accuracy score. We were just looking at that. Our accuracy is your true positive and your true negative over all of them. So how true is it? And there was our accuracy coming up here, 0.85. And then we have our nice matrix generated from that. And you can see right here is a similar matrix we had going for from the slide. And this should start asking questions at this point. So if you're in a board meeting or you're working with this, you really want to start looking at this data here and saying, well, is this good enough? Is this number of people, and hopefully you'd have a much larger data set, is my confusion matrix showing for the true positive and false positive, is that acceptable for what we're doing? And of course, if you're going to put together whatever data you're putting out, you might want to separate the true negative, false positive, false negative, true positive. And you can simply do that by doing the confusion matrix. And then, of course, the ravel part lets you set that up. So you can just split that right up into a nice tuple. And the final thing we want to show you here in the coding on this part is the confusion matrix metrics. And so we can come in here and just use the matrix equals classification report, the y-test and the predict. And then we're going to take that classification report and go ahead and print that out. And you can see here it does a nice job giving you your accuracy, your micro average, your weighted average, you have your precision, your recall, your F1 score, and your support all in one window, so you can start looking at this data and saying, oh, okay, our precision's at 0.83, 0.87 for getting a positive, and 0.83 for the negative side for a 0. And we start talking about whether this is a valid information or not to use. And when we're looking at a heart attack prediction, we're only looking at one aspect. What's the chances of this person having a heart attack or not? You might have something where we went back to the languages. Maybe you also want to know whether they speak English or Hindi or French. And you can see right here that we can now take our confusion matrix and just expand it as big as we need to, depending on how many different classifiers we're working on.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second
definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with the gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or our calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as the condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy.
Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is NumPy as NP. That's very standard when we're dealing with mathematics, especially with very complicated machine learning tools. You almost always see the NumPy come in for your numbers. It's called NumPython. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or OpenOffice Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in x equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database, so it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, I always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on. And then we put in our y predict en, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2 where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. So we have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree, but let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. it would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in two. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work. So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, there's very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. And we build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there, and let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal length, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data which tells us the answer for all these different pieces, and then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25%, we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans, and let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a Panda thing, the DF columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this like just like when we were up here and I typed in Y and it printed out Y instead of print Y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see injobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability. It generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually do, let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names, and we're going to run the prediction, and we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this, and this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising, since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those 2 characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats, it must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning, and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other? And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise-free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where, I mean, you might get into a gig of data if it's really clean, doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do it direct. There's also one that you look for your NaN. A lot of different options in here. But the NaN, numpy NaN is what that stands for, is doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NaN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you could see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up. But we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set. And let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down. And we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here. off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there with the actual running of our KNN. We need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using k-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the k-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have the and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
And find out why support vector machine. So in this example, last week my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you could figure out that it was a strawberry. So let's take this model a step further, and let's, why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of two categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the two groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where we have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have two groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in two lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a two-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a two-dimensional output. As you can see in this picture here, the 1D when transferred to a two-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a two-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a three-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data, whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These three advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo, and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout, and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here in the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice collection of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now, these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the np for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data, and we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals svm.svc kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our make blobs returns a NumPy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using 2 colors, 0, 1, and that's why we get the nice blue and the 2 different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a 3rd line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process 1 line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4 is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it, and you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
What is naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing 2 coins. Here we have 2 quarters, and if we look at all the different possibilities of what they can come up as, we get that they can come up as head-heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting 2 heads equals 1/4. You can see on our data set we have 2 heads, and it occurs once out of the 4 possibilities. And then the probability of at least 1 tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting 2 heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with 2 coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B and the second coin toss A. This can be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4 or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also a reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the two heads and two tails and head tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our three inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount? Yes or no. Did we have a free delivery? Yes or no. On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy? Yes or no. As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally we look at the probability of B if A. In this case we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all 3 independent variables. Now we can construct the likelihood tables for all 3 of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these 3 likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B, B being all three categories, did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on, and we're going to do 2 steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjusts for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walked through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since it's an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlibrary.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 newsgroups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 newsgroups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.targetNames. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. And let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58 in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let her know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the sklearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the tf-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the tf-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the tf-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. these are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here, from sklearn metrics, import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborne, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And then we have other variables that go into the SNS.heatmap. We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And then finally, we have our plt.x label. Remember, the SNS, or the seaborne, sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string, And then we're sending it train equals train. We have our training model, and then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predictS. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF, IDF vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF, IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is k-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into two clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily two characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want two clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation, where the centroid doesn't need any more repositioning. And that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, E, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with. And then as we progress, we keep changing until we get the best clusters. Or there is a technique called elbow technique whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that. And then the system will assign that many centroids. So it picks randomly that to start with randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point. And if required, the data points are reallocated to the new centroids and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart. So let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters. And for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign 2 centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. and then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids and so there are k groups. All these inputs have been split into k groups. However, remember we picked the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. Which means that the position of the randomly selected centroids will now change and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3 and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck and find whichever is the lowest distance and assign x2 to that centroid and so on. In this process there may be some reassignment. x1 was probably assigned to cluster C2 and after doing this calculation maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3 and so on up to ck, and then assign it to the point or to the centroid which has the lowest value and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python Notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually, also we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now, from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and it will create the clusters. So this is the code for that. We import k-means and then we create an instance of k-means and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4. And so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through, I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we call here, we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop, it only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but in the change will be very minor. So in that case also, that is actually convergence, right? So for example, the change is 0.0001, we can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically we have captured this information. So data is what, let me just show you here. Alright, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this, and so this is how the original, the color, the pixel distribution is. These are 2 plots, one is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in, the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these, this is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply this, the newly created colors, to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise, because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture, which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
So let's go a little deeper into hierarchical clustering. Let's consider we have a set of cars and we have a group similar. We want to group similar ones together. So below we have, you'll see 4 different cars down there. And we get 2 clusters of car types, sedan and SUV. So if you're just looking at it, you can probably think, oh yeah, we'll put the sedans together and the SUVs together. And then at last we can group everything into one cluster. So we just have just cars. So you can see as we have this, we make a nice little tree. This is very common when you see anybody talks about hierarchical clustering. This is usually what you see and what comes out of it. We terminate when we are left with only one cluster. So we have, as you can see, we bring them all together. We have one cluster. We can't bring it together anymore because they're all together. Hierarchical clustering is separating data into different groups based on some measure of similarity. So we have to find a way to measure what makes them alike and what makes them different. Agglomerative clustering is known as a bottom-up approach. Remember I said think of that as bringing things together? You see, I think the Latin term agglo is together because you have your agglomerate rocks where all the different pieces of rocks are in there. So we want to bring everything together. That's a bottom-up. And then divisive is we're going to go from the top down. So we take one huge cluster and we start dividing it up into 2 clusters, into 3, 4, 5, and so on. Digging even deeper into how hierarchical clustering works, let's consider we have a few points on a plane. So this plane is 2D, so we have an XY coordinates, kind of makes it easy. We're going to start with measure the distance. So we want to figure a way to compute the distance between each point. Each data point is a cluster of its own. Remember, if we're going from the bottom up, agglomerative, then we have each point being its own cluster. We try to find the least distance between 2 data points to form a cluster. And then once we find those with the least distance between them, we start grouping them together. So we start forming clusters of multiple points. This is represented in a tree-like structure called dendrogram. So there's another key word, dendrogram. And you can see it's just the branch that we've looked at before. And we do the second group the same, so it gets its own dendrogram, and the third gets its own dendrogram. And then we might group 2 groups together. So now those 2 groups are all under one dendrogram because they're closer together than the P1 and P2. And then we terminate when we are left with one cluster. So we finally bring it all together. You can see on the right how we've come up all the way up to the top. Whoops. And we have the gray hierarchical box coming in there and connecting them. So we have just one cluster, and that's a good place to terminate because there is no way we can bring them together any further. So how do we measure the distance between the data points? I mean, this is really where it starts getting interesting. Up until now, you can kind of eyeball it and say, hey, these look together. But when you have thousands of data points, how are we going to measure those distances? And there is a lot of ways to get the distance measure. So let's go ahead and take a look at that. Distance measures will determine the similarity between 2 elements, and it will influence the shape of the clusters. And we have Euclidean distance measure, we have squared Euclidean distance measure, which is almost the same thing but with less computations. And we have the Manhattan distance measure, which will give you slightly different results. And we have the cosine distance measure, which again is very similar to the Euclidean, playing with triangles. And sometimes it can compute faster depending on what kind of data you're looking at. So let's start with the Euclidean distance measure. The most common is we want to know the distance between the 2 points. So if we have point P and point Q, the Euclidean distance is the ordinary straight line. It is the distance between the 2 points in Euclidean space. And you should recognize D equals, in this case, we're going to sum all the points. So if there was more than 1 point, we could figure out the distance to the not more than 1 points. This is the sum of more than 2 dimensions. So we can have the distance between each of the different dimensions squared, and that will give us, and then take the square root of that, and that gives us the actual distance between them. And they should look familiar from Euclidean geometry. Maybe you haven't played too much with multiple dimensions, so the summation symbol might not look familiar to you. But it's pretty straightforward as you add the distance between each of the 2 different points squared. So if your y difference was 2 minus 1 squared would be 2, and then you take the difference between the x, again squared, and if there was a z coordinates, it would be z1 minus z2 squared, and then take the square root of that and sum it all together, and then take the square root of it. So to make it compute faster, since the difference in distances, whether one is farther apart or closer together than the other, we can do what's called the squared Euclidean distance measurement. This is identical to the Euclidean measurement, but we don't take the square root at the end. There's no reason to. It certainly gives us the exact distance, but as far as doing calculations as to which one's bigger or smaller than the other one, it won't make a difference. So we'll just go with so we just get rid of that final square root. It computes faster, and it gives us pretty much the Euclidean squared distance on there. Now, the Manhattan distance measurement is a simple sum of horizontal and vertical components, or the distance between 2 points measured along axes at right angles. Now this is different because you're not looking at the direct line between them. And in certain cases, the individual distances measured will give you a better result. Now generally that's not true. Most times you go with the Euclidean squared method because that's very fast and easy to see. But the Manhattan distance is you measure just the y value and you take the absolute value of it, and you measure just the x difference and you take the absolute value of it, and just the z. And if you had more, different dimensions in there, A, B, C, D, E, F, however many dimensions, you would just take the absolute value of the difference of those dimensions. And then we have the cosine distance. Similarity measures the angle between the 2 vectors. And as you can see, as the 2 vectors get further and further apart, the cosine distance gets larger. So it's another way to measure the distance. Very similar to the Euclidean, so you're still looking at the same kind of measurement, so it should have a similar result as the first two. But keep in mind the Manhattan will have a very different result, and you can end up with a bias with the Manhattan if your data is very skewed, if one set of values is very large and another set of values is very small. But that's a little bit beyond the scope of this. It's just important to know that about the Manhattan distance. So let's dig into the agglomerative clustering. And agglomerative clustering begins with each element as a separate cluster, and then we merge them into a larger cluster. How do we represent a cluster of more than one point? So we're going to kind of mix the distance together with the actual agglomerative and see what that looks like. And we're actually going to have three key questions that are going to be answered here. So how do we represent a cluster of more than one point? So we want to look at the math, what it looks like mathematically and geometrically. How do we determine the nearness of clusters? When to stop combining clusters? Always important to have your computer script or your whatever you're working on have a termination point so it's not going on eternally. We've all done that if you do any kind of computer programming or writing a script. Let's assume that we have 6 data points in a Euclidean space. So again, we're dealing with x, y, and z. In this case, just x and y. So how do we represent a cluster of more than one point? Let's take a look at that. And first we're going to make use of centroids. Very common terminology in a lot of machine learning languages when we're grouping things together. So we're going to make use of centroids, which is the average of its points. And you can see here we're going to take the 1, 2 and the 2, 1 and we're going to group them together because they're close. And if we were looking at all the points, we'd look for those that are closest and start with those. And we're going to take those two and we're going to compute a point in the middle. And we'll give that point 1.5, 1.5. And that's going to be the centroid of those 2 points. And next we start measuring like another group of points. We got 4, 1, 5, 0. When they're pretty close together. So we'll go ahead and set up a centroid of those 2 points. In this case it would be the 4.5 and 0.5 would be the measurements on those 2 points. And once we have the centroid of the 2 groups, we find out that the next closest point to a centroid is over on the left. And so we're going to take this and say, oh, 0, 0 is closest to the 1.5, 1.5 centroid. So let's go ahead and group that together. And we compute a new centroid based on those 3 points. So now we have a centroid of 1.1 or 1, 1. And then we also do this again with the last point, the 5, 3, and it computes into the first group. And you can see our dendrogram on the right is growing. So we have each of these points are become connected and we start grouping them together. And finally we get a centroid of that group too. And then finally the last thing we want to do is combine the 2 groups by their centroids. And you can see here we end up with one large group and it'll have its own centroid, although usually they don't compute the last centroid. We just put them all together. So when do we stop combining clusters? Well, hopefully it's pretty obvious to you. In this case, when they all got to be 1. But there are actually many approaches to it. So first, pick a number of clusters k up front. And this is done in the fact that we don't want to look at 200 in clusters. We only want to look at the top 5 clusters or something like that. So we decide the number of clusters required in the beginning and we terminate when we reach the value k. So if you looked back on our clustering, let me just go back a couple screens. You'll see how we clustered these all together, and we might want just the 2 clusters. And so we look at just the top 2. Or maybe we only want 3 clusters. And so we would compute which one of these has a wider spread to it or something like that. There's other computations to know how to connect them. And we'll look at that in just a minute. But to note that when we pick the k value, we want to limit the information that's coming in. So that can be very important, especially if you're feeding it into another algorithm that requires 3 values, or you set it to 4 values, and you need to know that value coming in. So we might take the clustering and say, okay, only 3 clusters. That's all we want for k. So the possible challenges, this only makes sense when we know the data well. So when you're clustering with k clusters, you might already know that domain and know that that makes sense. But if you're exploring brand new data, you might have no idea how many clusters you really need to explore that data with. Let's consider the value of k to be 2. So in this case, in our previous example, we stop when we are left with 2 clusters. And you can see here that this is where they came together the best while still keeping separate the data. The second approach is stop when the next merge would create a cluster with low cohesion. So we keep clustering till the next merge of clusters creates a bad cluster low cohesion setup on there. That means the point is so close to being between 2 clusters, it doesn't make sense to bring them together. But how is cohesion defined? Oh, let's dig a little deeper into cohesion. the diameter of a cluster. So we're looking at the actual diameter of our cluster, and the diameter is the maximum distance between any pair of points in the cluster. We terminate when the diameter of a new cluster exceeds the threshold. So as that diameter gets bigger and bigger, we don't want the two circles or clusters to overlap. And we have radius of a cluster. Radius is the maximum distance of a point from centroid. We terminate when the radius of a new cluster exceeds the threshold. Again, we don't want things to overlap, so when it crosses that threshold and is overlapping with other data, we stop. So let's look at divisive clustering. Remember, we went from the bottom up, now we want to go from the top down. Divisive clustering approach begins with a whole set and proceeds to divide it into smaller clusters. So we start with a single cluster composed of all the data points. We split it into different clusters. This can be done using monothetic divisive methods. What is a monothetic divisive method? And we'll go backwards and let's consider the example we took in the agglomerative clustering to understand this. So we consider a space with 6 points in it, just like we did before, same points we had before. And we name each point in the cluster. So we have, in this case, we just gave it a letter value, A, B, C, D, E, F. Since we follow top-down approach in divisive clustering, obtain all possible splits into 2 columns. So we want to know where you could split it here. And we could do like a AB split and a CDEF split. We could do BCE, ADF, and you can see this starts generating a huge amount of data. ABCDEF. And so for each split, we can compute cluster sum of squares. And we can see here, actually have the formula out for us, BJ12 equals N1 of absolute value of x minus absolute value of x squared. So again, we're computing all the different distances in there squared, back to your kind of Euclidean distances on that. And so we can actually compute B of j between clusters 1 and 2. And we have the mean of the cluster and the grand mean, depending on the number of members in the cluster. And we select the cluster with the largest sum of squares. Let's assume that the sum of squared distance is largest for the third split we had up above, and that's where we split the ABC out. And if we split the ABC out, we're left with the DEF on the other side. We again find the sum of squared distances and split it into clusters. So we go from ABC, we might find that the A splits into BC and D into EF. And again, you start to see that hierarchical dendrogram coming down as we start splitting everything apart. And finally, we might have A splits in B and C, and then each one gets their own DEF. And it continues to divide until we get little nodes at the end and every data has its own point. Or until we get to K, if we have set a K value. So we've kind of learned a little bit about the background and some of the math in hierarchical clustering. Let's go ahead and dive into a demo. And our demo today is going to be, for the problem statement, we're going to look at U.S. oil. So a U.S. oil organization needs to know its sales in various states in U.S. and cluster the states based on the sales. So what are the steps involved in setting this problem up? So the steps we're going to look at, and this is really useful for just about any processing of data, although I believe we're going to be doing this in R today. We're going to import the data set. So we'll explore our data a little bit there. Create a scatter plot. It's always good to have a visual if you can. So once you have a visual, you can know if you're really far off in the model you choose to cluster the data in or how many splits you need. And then we're going to normalize the data. So we're going to fix the data up so it processes correctly. We'll talk more detail about normalization when we get there. And then calculate the Euclidean distance. And finally, we'll create our dendrogram so it looks nice and pretty and we have something we can show to our shareholders so that they have something to go on and know why they gave us all that money in salary for the year. So we go ahead and open up R, and we're actually using R Studio, which is really has some nice features in it. It automatically sets up the 3 windows where we have our script file on the upper left, and then we can execute that script and it'll come down and put it into the console bottom left and execute it. And then we have our plots off to the right, and I've got it zoomed in, hopefully not too large a font but large enough that you can see it. And let's just go ahead and take a look at some of the script going in here. It's clustering analysis, and we're going to we'll call it my data, and we're going to assign it in R. This is a symbol for assigning. And we're going to go read CSV. Read CSV file. And we'll put that in brackets. And before we go any further, let's just look at the data outside of R. It's always nice to do if you can. And the file is going to be called utilities.csv. This would also be the time to get the full path, so you have the right path to your file. And remember that you can always post in the comments down below. And when you post down there, just let us know you want to connect up with Simplilearn so that they can get you this file, so you can get the same file we're working on and you can repeat it and see how this works. This is utilities.csv. It's a comma-separated variable file, so it's pretty straightforward. And you can see here they have the city, fixed charge, and a number of different features to the data. And so we have our ROR, cost, load, demand, cells, nuclear fuel cost on here. And then going down the other side, we have U.S. cities, Arizona, Boston. They have central U.S., so I guess they're grouping a number of areas together. The Commonwealth area, you can see down here, Nevada, New England, northern U.S., Oklahoma, the Pacific region, and so on. So we have a nice little chart of different data they brought in. And so I'm going to take that complete path that ends in the utilities.csv, and we're going to import that file. Let me just enlarge this all the way. Oops, I had an extra set of brackets here somehow. Or maybe I missed a set of brackets. This can happen if you're not careful. You can get brackets on one side and not the other, or in this case, I got double brackets on each side. There we go. And then the magic hotkeys in this case are your Control-Enter, which will let me go ahead and run the script. And so I've now loaded the data, and as you can see, I went ahead and shrunk the plot since we're going to be looking at the window down below. And we can simply convert the data to a string. Now, all of us do this automatically the first time. We say, hey, just print it all out as a string. And then we get this huge mess of stuff that doesn't make a whole lot of sense. So, and you can see here they have, you can probably kind of pull it together as looking at it. But let's go ahead and just do the head. And we'll do the head of my data. There we go. And Control-Enter on that. And the head shows the first 5 rows. You'll see this in a lot of different scripts. In R, it's you type in head and then in brackets you put your data. And it comes through and lists the first 5 rows as you can see below. And it shows Arizona, Boston, Central, and it has the same columns we just looked at. So we have the fixed charge, the ROR, the cost, the load, the D demand. I'm not an expert in oil, so I'm not even sure what D demand is. Cells, I'm guessing nuclear, how much of it's supplied by nuclear, and the actual fuel cost. And then the different states that it's in or different areas. And one of the wonders of R is all these cool, easy to use tools that are so quick. So we'll do pairs. And pairs creates a nice graph. So let me go ahead and run this. Whoops. The reason it gave me an error is because I forgot to resize it. So let me bring my plot way out so we can see it. And let's run that again. And you'll see here that we have a nice graph of the different data and how it plots together, how the different points kind of come together. This is neat because if you look at this, I would look at this and say, hey, this is a great candidate for some kind of clustering. And the reason is when I look at any 2 pairs, let's go down to, say, cells and fuel cost towards the bottom right. And when you look at them where they cross over, you sort of see things how they group together, but it's a little confusing. You can't really pinpoint how they group together. You could probably look at these 2 and say, yeah, there's pretty good commonalities there. And if you look at any of the other pairs, you'll start seeing some patterns there also. And so we really want to know what are the patterns on all of them put together, not just any 2 of them, but the whole setup. Let me go ahead and shrink my this down for just a second, just a notch here. And let's create a scatter plot. Oops. And this is simply just use the term plot in brackets, and then which values do we want to plot. And if we remember when we looked at the data earlier, let me just go back this way. In this case, let's go ahead and compare just two values to see how they look. And we'll do fuel cost and cells, and it's in my data. So we got to let it know which 2 columns we're looking at next to each other. And it will open up our plot thing and then go ahead and execute that. And we can see on those close up of what we were just looking at in the pairs. And if I was eyeballing this, I would say, oh look, there's a kind of a cluster up here of 5 items, and this one is hard to tell which cluster it'd be with, but maybe it's 6 to go in the top one, and you have a middle cluster and a bottom cluster, maybe two different clusters. So you can sort of group them together, fuel cost and the cells, and see how they connect with each other. And again, that's only two different values we're looking at. So in the long run, we want to look at all of them. And then the people in the back, they sent me the script so we can go ahead and add labels. So with my data text, fuel cost cells, the labels equals city, position 4. These are numbers you can kind of play with till they look nice. And oops, again I forgot to resize my plot. It doesn't like having it too small. And we'll run that. I mistyped something in here. Oh, I did a lowercase d and they did a capital D. There we go. So now we can go in here and do this with my data. And you can see, a little hard to see on my screen with all the different things in there. It plots the actual cities. So we can now see where all the cities are in connection with, in this case, fuel cost and cells. So you have a nice label to go with the graph. And then we can also go ahead and plot, in this case, let's do, the ROR, oops. And we'll do that also with the cells, and do my data. Remember to leave it lowercase this time. So when we plot those two, we'll come over here, and it's going to, I'm surprised it didn't give me an error. And then we'll also add in the with statement, so we put some nice labels in there. And it's going to be the same as before, except instead of doing the fuel cost cells, we want the R cells. And we'll execute that. Oops, and of course it gives me an error because I shrunk it down. So let's redo those two again. There we go. And we can see now we have the ROR with cells. And we'd probably get a slightly different clustering here if I was looking at these cities. They're probably different than what we had before. But you could probably look at this and say, these kind of go together and those kind of go together. But again, we're going to be looking at all of them instead of just one or two. And so at this point, we want to dive into the next step, where we're going to start looking at a little bit of coding or scripting here. This is very important because we're going to be looking at normalization. We put that in there, normalization. And if you've done any of the other machine learning skills and setup, this should start to look very normal in your pre-processing of data. Whether you're in R or Python or any of these scripts, we really want to make sure you normalize your data so it's not biased. Remember, we're dealing with distances, and if I have, let's say the ROR is, even look at this graph here on the right, you can see where my ROR varies between 8 and 14. That's a very small variable. And our cells varies between 4,000 and 16,000. So you can imagine the distance between 4,000 and 8,000, which is the distance of 4,000, versus 8 to 10 versus 2, the cells is going to dominate. So if we do any kind of special work on this, it's going to look at cells and it's going to cluster them just by the cells alone. And then ROR might have a little tiny effect of 2 versus 4,000. We want to level the playing field. Turns out there's actually a number of ways in script to normalize. So I'm just going to put in the code that they put together in the back for me. And let's talk about it a little bit. So we have Z, we're going to assign it to my data. And it's go ahead and we're going to do a little reshaping across all rows. Or across all columns. So each of the rows is going to have a little reshaping there. And then we're going to get M, which stands for means. And we're going to apply it to my data. So again, we want to go ahead and create the most common variable in there. And then S is going to be, SD stands for standard deviation. So instead of just doing, a lot of times what they do with normalization of data is we just reshape the data everything between 0 and 1. So that if the lower end is 8, that now becomes 0, and the upper end is 14, that now becomes 1. That doesn't help if it is not a linear set of data. So with this, we're going to look for the means and the standard deviation for reshaping the data. And that way, the most common values now become the kind of like the center point. And then the standard deviation is how big the spread. So we want the standard deviation to be equal amongst all of them. And then finally we go ahead and take Z, and with the Z we're going to reassign it, and we're going to scale the original my data, which we reshaped, based on M and based on the standard deviation. And the 2 in here, that just means we're looking at everything in kind of a XY kind of plot. And we can quickly run these. Control Enter, Control Enter, Control Enter, Control Enter. So now we have Z, which is a scaled version of my data. And now we can go ahead and calculate the Euclidean distance. Oops, calcu. There we go. And in R, this is so easy. Once you've gotten to here, we've done all that pre-data processing. We'll call it distance. And we'll assign this to dist. So dist is the computation for getting the Euclidean distance. And we can just put Z in there because we've already reformatted and scaled Z to fit what we want. Let me go ahead and just hit enter on that. And I'm going to widen my left-hand side again. I'm always curious, what does this data look like? So let's just type in distance, which will print the variable down below. Oops. You have to hit Control Enter. And this prints out a huge amount of information. As you can see, it just kind of streams down there. And let's go ahead and enlarge this. And I don't know about you, but when I look at something like this, it doesn't mean a whole lot to me, other than I see 2, 3, 4, 5, 6, and then you kind of have the top part, 6, 17, 18. So imagine this is like a huge chart, is what we're looking at. And we can go ahead and use print, distance, digits equal 3. And let's run that. Oops, I keep forgetting that it has to go through the graph on the right. And we see a slightly different output in here. Let me just open this up so we can see what we're looking at. And by cutting down the distance, you can start to see the patterns here of it's looking at the different distances. So if I go to the top, we have the distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 2 and 3, and so on. Obviously, the distance between itself is 0. And it doesn't repeat the data, so we don't care to see 2 versus 1 again, because we already know the distance between 1 and 2. And so we have a nice view of all the distances in the chart, and that's what we're looking at right here. And it's a little easier to read. That's why we did the print statement up here to do digits equals 3, make it a little bit smaller. We could even just do digits. Let's just do 2, see what that looks like. We might lose some data on this one if something's way off. But we have a nice setup and we can see the different distances, and that's what we computed here between each of the points. And then the whole reason we're doing this is to get ourselves a nice dendrogram going, a nice clustering dendrogram. We'll do a couple of these looking at different things. We'll take a variable hc.l and we're going to assign it h cluster and then distance. That easy. We've already computed the distances. So the H clustering does all the work for us. And let me hit enter on there. So now we have our HCL, which is assigned the H clustering computation based on distances and apart. And then I'm going to expand my graph because we would like to go ahead and see what this looks like. And we can simply plot that and hit the Control Enter so it runs. And look at that. We have a really nice clustering dendrogram. Except when I look at it, the first thing I notice is it really shows like numbers down below. Now, if you were a shareholder and some data scientist came up to you and said, look at this is what it means, you'd be looking at that going, what the heck does 3, 9, 14, 19, 1, 18 mean? So let's give it some words there. So let's do the same plot with our HCL. HC, there we go. And let's add in labels. And this is just one of the commands in plots. So we have labels equals my data. And then under my data, we want to know the city. And we'll have it hang -1. That's just the instructions to make it pretty. So we'll run that. Oops, I accidentally ran just hang my 1. Let me try that again. There we go. Okay, so now you can see what it's done, and the Hang My one turns it sideways. That way we can see Central, which is Central U.S. and Kentucky, and we start to actually get some information off our clustering setup. And the information you start looking at is that when we put all the information together, you probably want to look at Central America and Kentucky together. Oklahoma and Texas has a lot of commonality, as does Arizona and Southern U.S. And you could even group all 5 of those: Florida, Oklahoma, Texas, Arizona, and Southern U.S. These regions, for some reason, share a lot of similarities. And so we want to start asking what those similarities are. But this gives us a place to look. It says, hey, these things really go together. You should be grouping these together as far as your cells and what you're doing. And then one of the things you might want to do is we can do the dendrogram average. And this changes how we do the clustering. So it looks very similar like we had before. And there's our HCl. We're going to assign it. We're going to do an H cluster. We're still doing it on distance. Oops, distance. And this time we're going to set the method to average. So we can change the methodology in which it computes the values. And before, if you remember correctly, we did median. Median's a little bit different than means. We did the most common one, and then we want the average of the median. And let's go ahead and run that. And then we can plot. And here's our HCl. Oops, there we go. Here's our HCl, and I can run that plot. And you can see this changed a little bit. So our way it computes and groups things looks a little different than it did before. And let's go ahead and put the cities back in there and do the hang. Control copy. Let me just real quickly copy that down here, because we want the same labels. And again, you can see Nevada, Idaho, Puget. I remember we were looking at Southern U.S. and Arizona, Texas and Oklahoma, Florida. So the grouping really hasn't changed too much. So we still have a very similar grouping. It's almost kind of flipped it as far as the distance based on average has. But this is something you could actually take to the shareholders and say, hey, look, these things are connected. And at which point you want to explore a little deeper as to why they're connected, because they're going to ask you, okay, how are they connected and why do we care? But that's a little bit beyond the actual scope of what we're working on today. But we are going to cover membership, what's called clustering membership on there. And let's create a member. We'll just call it member 1. Oops, there, member.1. And we're going to assign to this, we're going to do cut tree. And cut tree, it limits it. So what that means is I take my hc.l in here. Oops, there we go, .l. And so I'm taking the cluster I just built, and we want to take that cluster, and we want to limit it to just a depth of 3. So we go ahead and do that, and run that one. Oops, let me go run. There we go. So now I've created my member 1. And then, whoops, let me just move this out of the way. We're going to do an aggregate, and we're going to use Z, remember Z from above, and we're going to turn member 1 into a list, and then we're going to aggregate that together based on the mean. Let me go ahead and enter, run that. Oops, I did member L, it's actually member 1. There we go. And if we take a look at this, we now have our group 1 fixed charge, and then all your different columns listed there. And most of them should come up kind of looking between 0 and 1, but you'll see a lot of variation because we're varying it based on the means. So it's the means, the standard deviation, not just forcing it in between 0 and 1, which is a much better way usually to normalize your data than just doing the 0-1 setup. And finally, we can actually look at the actual values, and the same chart we just did. Oops. I made a mistake on there with my data. There we go. Okay. And again, we now have our actual data instead of looking at just if you looked up here, it's all between 0 and 1. And when we look down here, we now have some actual connections and how far distance this different data is. Again, becomes more of a domain issue and understanding the oil company and what these different values means. And you can look at these as being the distances between different items. So a little bit different view, and you have to really dig deep into this data. What we really want you to take away from this is the dendrogram and the charts that we did earlier. And that is the cluster output and our nice dendrogram. So this would be stage 1 in data analysis of the cells. Again, you'd have to have a lot more domain experience to find out what all the individual numbers we looked at mean and what the distance is and what's difference between Central America and Kentucky and why they're similar and why it groups all of Central Kentucky, Florida, Oklahoma, Texas, Arizona, and Southern U.S. together into one larger group. So that'd be way beyond the scope of this. But you can see how we start to explore data and we start to see things in here where things are grouped together in ways we might not have seen before. And this is a good start for understanding and giving advice for sales and marketing, maybe logistics, city development. There's all kinds of things that kind of come together in the hierarchical clustering as you begin to explore data. And we just want to point out that we get 3 clusters of regions with the highest cells, region with average cells, region with the lowest cells. Again, those are some of the things that they clustered it around, and you could actually see where things are going on or lacking. In this case, if you're the lowest cells, no one wants to be in the region of the lowest cells.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
A regression algorithm is used to find out the connection between dependent and independent variables. Dependent variables are nothing but a variable that we are trying to predict or forecast, and independent variables are the factors that influence the analysis. It is usually used to make projections. Medical researchers frequently utilize linear regression to study the connection between patient blood pressure and dosage. Researchers may give patients different quantities of a specific medication and track how their blood pressure changes. A regression model might use dosage as a predictor variable and blood pressure as a response variable. There are some popular regression algorithms that come under supervised machine learning. First one is linear regression, regression trees, nonlinear regression, Bayesian linear regression. After discussing what is supervised learning and its types, let's move forward to see what actually regression analysis is. A stat technique known as regression analysis is used to simulate the relationship between dependent and independent variables using one or more independent variables. Regression analysis more precisely enables us to comprehend and when other independent variables are held constant. Changes in the dependent variable's value that correspond to an independent variables are changing. Predictions include values that are continuous or real, such as temperature, age, pay, and cost. There are some following concepts or terminologies that must be understood in order to completely grasp regression analysis. The first one is dependent variable. In a regression analysis, the primary variable we wish to predict or comprehend is the dependent variable. Here, dependent variables are also known as target variable. The next one is independent variable. The term independent variables, also known as predictor, refers to the elements that impact the dependent variables or are used to forecast their values. And the third one is outliers. An observation that is extremely high or extremely low in relation to the other observed values is referred as an outlier. An outlier should be avoided as it might affect the outcomes. The fourth one is multicollinearity. The situation is said to as occurring when independent variables have a higher correlation with one another than other variables. It shouldn't be included in the dataset because it causes issues when determining which variable has the greatest impact. And the fifth one is overfitting and underfitting. Overfitting is the problem that occurs when our system performs well with the training dataset but poorly with the test dataset. Underfitting is the term used when an algorithm does not perform well even with the training dataset. After understanding what regression analysis is and its terminologies, let's move forward and see why we use regression analysis, including those involving the weather, sales, marketing trends, and other factors. In this situation, we need regression analysis that can make forecasts more precisely. So let's understand the concept of regression analysis using an example. Business frequently use linear regression to understand the relationship between advertising spending and income. For instance, they might run a simple linear model with advertising as a response variable and revenue as a predictor variable. The regression model would look like this. Revenue equals to beta 0 plus b1 ad spending. Where there are no advertising, the coefficient 0 would indicate the whole expected revenue. When advertising expenditures are increased by 1 unit, coefficient will represent the typical change in the total revenue, that is $1. If beta 1 is negative, then higher advertising expenditures will result in lower revenue. If beta 1 is nearly 0, advertising expenditures have little impact on revenue. And if beta 1 is positive, it would imply that more advertising expenditures are linked to higher income. The amount of beta 1 will determine whether a corporation decides to or decrease its advertising budget. Regression means creating a graph that connects variables the best fit the given data point. The regression analysis model can then make prediction about data using the plot. Regression analysis is defined as showing a line or a curve that goes through all the data points on the target predictive graph in such a way that vertical distance between the data points and the regression is smallest. Whether a model has captured a strong link between determined by the distance between data points and the line. There are some more use cases of regression analysis, like we can use temperature, another variable, to predict or forecast rain. Regression analysis can be used for identification of market trends. For predicting traffic accidents caused by reckless driving, we can use regression analysis for the same and many more. So by understanding why we need regression analysis, moving forward, let's see some popular regression algorithms in detail. The first one is linear regression. Linear regression is one of the most famous and straightforward machine learning algorithms utilized for predictive analysis. Linear regression shows the linear connection between dependent and independent factors. The line of the equation is y equals to mx plus b. Here, y stands for the response variable or a dependent variable, whether x is for the predictor variable or an independent variable. Here, m is the estimated slope and b is for the estimated intercept. And the next one is regression trees. A regression tree is worked through a cycle known as binary recursive, which is iterative interaction that divides the information into segments or branches, and afterward keep splitting the data into smaller groups. As the technique climbs each branch, this tree is used for the dependent variable with continuous values. For example, a regression tree name food, which is divided into segments, veg and non-veg. Further, it keeps splitting into smaller groups. And the third one is nonlinear regression. Nonlinear regression is a type of regression examination wherein information is to fit a model and afterward communicated with a numerical function. Simple linear regression relates two factors x and y with a straight line y equals to mx plus b, while nonlinear regression relates the two factors in a nonlinear relationship. Nonlinear regression can be predict population growth over time or the relationship between GDP and a country's time. And the fourth one is Bayesian linear regression. The algorithm is a way to deal with a linear regression in which statistical examination is attempted inside the setting of Bayesian inference. Linear regression and Bayesian regression can generate the same prediction, and with the help of Bayesian processing, we can retrieve the complete variety of inferential solution instead of a point estimate. After seeing some regression analysis algorithm, let's move forward and see advantages and disadvantages of different regression analysis models. And the first model is linear regression model. The advantages are work well irrespective of dataset size. And the second one is gives information about the relevance of features. And the disadvantages are the assumptions of linear regression. And the next one is polynomial regression. The advantages are works on any size of the dataset. And the second one is works very well on non-linear problems. And disadvantages are we need to choose the right polynomial degree for the variance trade-off. The next one is support vector regression algorithms, and the advantages are easily adaptable, works very well on non-linear problems, and disadvantages are difficult to understand and not well known. And the next one is decision tree regression. The advantages of decision trees are no need to apply scaling, and the second one is works very well on both linear and non-linear problems. And disadvantages are poor results on a small dataset and overfitting can easily occur. And the last one is random forest regression. The advantages are powerful and second one is accurate. And disadvantages are no interpretability and the second one is overfitting can easily occur. After seeing advantages and disadvantages of different types of regression analysis models, let's move forward and see some applications of regression analysis. The first one is forecasting. Regression analysis is frequently used in business to predict potential opportunities and dangers. For example, demand analysis predicts how many items a buyer is likely to purchase. Demand, however, is not only the dependent variables when it comes to business. Much more than just direct income can be predicted using regression analysis. And the second one is CAPM, Capital Asset Pricing Model. The linear regression model is a key component of the capital asset pricing model, CAPM, which determines the relationship between an asset expected return and the associated market risk premium. Financial analysts typically use it for forecast corporate return and operational performance when doing financial analysis. And the third one is comparing with competition. It can be used to evaluate how well a business is doing financially in comparison to a certain rival. It can also be used to figure out how the stock prices of two companies are related to one another. This can be extended to find the correlation between two competing companies. It might help the company identifying the factors affecting the sales in contrast to the comparable company. These methods can help small business succeed quickly within a short period of time. And the last one is identifying problem. Regression is beneficial for identifying incorrect judgment as well as for providing factual support for the management. For instance, a retail store manager might believe that extending the hours of operation will greatly increase sales.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
So let's go ahead and talk about overfitting. When we talk about overfitting, it's a scenario where the machine learning model tries to learn from the details along with the noise, and the data tries to fit each data point on the curve. You can see that if you plug in your coordinates, you're just going to get the whatever is fitted every point on the data stream. There's no average. There's no 2 points that might have the, Y might have two different answers because if the wind blows a certain way and your efficiency of your car, maybe you have a headwind, so your car might alter how efficient it is as it goes, and so there's going to be this variance on here, and this says no, you can't have any variance with it's going to be exactly this. So it can't be you can't be the same speed or the same car and have a slightly different efficiency. So as the model has very less flexibility, it fails to predict new data points, and thus the model rejects every new data point during the prediction. So you'll get like a really high error on here. And so reasons for overfitting. Data used for training is not cleaned and contains noise, garbage values in it. You can spend so much time cleaning your data, and it's so important. It's so important that if you have something wrong with the data coming in, it needs to be addressed. Whether it's the source of the data, maybe they use in medical different measuring tools. So you now have to adjust for data that came in from hospital A versus hospital B, or even off of machine A and machine B that's testing something, and those numbers are coming in wrong. The model has a high variance. Again, wind is a good example. I was talking about that with the car. You may have 100 tests, but because the wind's blowing, it's all over the place. Size of training data used is not enough, so a small amount of data is going to also cause this problem. You only have a few points and you try to plot everything. The model is too complex. This comes up a lot we put too many pieces together, and how they interact can't even be tracked. And so you have to go back, break it up, and find out actually what correlates and what doesn't. So, what is underfitting? A scenario where machine learning models can neither learn the relationship between the data points nor predict or classify a new data point. And you can see here we have our efficiency of our car and our line drawn, and it's just going to be way off for both the training and the predicting data. As the model doesn't fully learn the patterns, it accepts every new data point during the prediction. So instead of looking for a general pattern, we just kind of accept everything. Data used for training is not cleaned and contains noise, garbage, and values. Again, underfitting and overfitting, same issue. You got to clean your data. The model has a high bias. We've seen this in all kinds of things, from the most common is the driving cars to facial identification or whatever it is. The model itself, when they build it, might have a bias towards one thing. And this would be an underfitted model, would have that bias because it's averaged it out. So if you have 5 people from India and 10 people from Africa and 20 people from the US, you've created a bias because it's looking at the 20 people, and you only have a small amount of data to work with. Size of training data used is not enough. That goes with the size I was just talking about. So we have a model with a high bias, we have size of training data used is not enough. The model is too simple. Again, this is one straight line through all the data when it has a slight shift to it for other reasons. So what is a good fit? A linear curve that best fits the data is neither overfitting or underfitting models, but is just right. And of course we have the nice examples here where we have overfitting, lines going up and down, every point's trying to be included. Underfitting, the line really is off from where the data is, and then a good fit is got to get rid of that, minimize that error coming through. So this is all exciting, but what does this look like? So we really need to jump in and put a code together and see what this looks like when we're programming. For this demo, we'll bring up our trusty Anaconda and go into Jupyter Notebook for Python. Move myself out of the way here. And so we're going to start off, this is going to be a demo on overfitting and underfitting using Python. And let's start with our imports. Now, if you've been through enough of these tutorials, we don't want to spend a huge amount of time on what we're bringing in and what we're doing. So you should be up on doing this with Python and how to bring in your different modules. We're going to bring in the sklearn, or the scikit processing, sklearn.neural network, import MLP regressor. So there's our regressor model right there. That's going to be our linear regression model. And we have our metrics, mean, absolute error. If you remember, we had our, that's how we figure out how well it fits, is how far off that error is based on the mean square error value, MSE. And then, of course, NumPy, because we just like to work with NumPy. It's a great data array. We always import it as MP. That's the most common way of doing it. And then we have sklearn model selection, import validation curve. So we're going to look at a validation curve to see how good our models are. And then we have the data set. We'll use the very famous iris data set, and that's embedded in the scikit. So the sklearn data sets have a load iris in there. And then we have the matplot library, because if you're doing any kind of demo or showing this off to your shareholders, we want to have something nice to display it on. And then we have sklearn model selection. We're going to import kfold. And we'll talk about that when we get to it. And then we're going to go ahead and do, just for our NumPy, we're going to do like a random seed for random numbers. And then for our plot style, we'll use the ggplot. That's just some back-end setup. You could even probably leave the plot style out, depending on what version of you're using of, depending on what version you're using of matplot library. And then we'll go ahead and run this. It's not going to do anything that we can visibly see, because it's just loading those modules. And then we also want to load our iris data in here. and the iris data has an iris data and an iris target. We're going to load that as X and Y. And just so you can have an idea what we're talking about, we're going to go ahead and print X, and just the first bit of X, we'll just do the top of X, and we'll also print Y, so you can see what the top of Y looks like. Print Y. And since we're in NumPy, we're going to go ahead and do our own thing. If this was, of course, Pandas, we could just do the head of it and see what it looks like. And you can see here we've loaded this up, and in X we have these different measurements that they take of the flower, the iris flowers from this particular data set, and what kind of flower it is. It's going to be a 0, a 1, or a 2 is actually what the target comes out of, even though that doesn't show in here. And so we're going to come in here and we're going to use the k-folds cross-validation with 20 folds. And a good catch that this was a model selection. We're going through and we're selecting different parts of the data in here. Here we use k-folds cross-validation with 20 folds, k equals 20, to evaluate the generalization efficiency of the model. Within each fold, we will then estimate the training and test error using the training and test sets respectively. So here we have our kf equals k-fold. Here's our splits on the top. And then we need to go ahead and have our list training error. We're going to create an array for that. We're going to list our testing error. And for train index and test index in kf.splitx, xtrain, xtrain and xtest, we're going to go ahead and split up our data, our x values, and the same thing with the y values. So now we have an xtrain and an xtest, a ytrain and a ytest. And then here's our model, our MLP regressor. And that's your linear regressor model in there. And we have used a multi-layer perceptron, MLP. So this is a neural network, multi-layer perceptron. That's what the MLP is for. Regressor means that it is dealing with numbers. We're not categorizing things. And then let's go ahead, kind of went off the screen here. We'll just go ahead and bring that down. It's a class of feed-forward artificial neural networks. And they kind of loosely call it ANN. Don't get caught up in the ANN, NNN, MNN. There's NN is neural network, and then everybody puts their own flavor on it depending on what they're doing. So if you see the NN, you know you're dealing with a neural network. So we go ahead and fit our data. Here's our model.fit. We have xtrain and ytrain. And the ytrain data we're going to predict equals model.predict xtrain. So here's our prediction of what it's going to be. So we've trained it and we predicted it. We've trained it the train data, and then we have our ytrain. And then we have our ytest. And the ytest equals a model predict xtest. Now notice what we did here is we're going to use our model to predict what we think y should be, but this is the training set. So we've trained it with this data, and now we want to see how good our model fits our training data. And then we want to see how well it fits our testing data. So we take our fold training error, mean absolute error, ytrain data predict, and we're going to do our fold testing error, the mean absolute error of ytest and ytest data predict. And we do this, and here's our mean absolute error. There's our a little bit different connotation, but that's taking the square value and finding in this case it's using the absolute value. So instead of the square value, we get rid of the minus and pluses by using an absolute value. And we find the average of that. And that works the same way as doing the squared value. And then we take our list training error, and we're going to go ahead and just append it for each one of these runs we go through. So every time we fold the data, think of it like this. We want to go ahead and take a piece of data. That's going to be one piece of the data, and we're going to look at each section. And we want to go through each section to see how well it does and splits it up. This way we have a nice picture when we're looking at it from a distance. I do this a lot when I do when I split my X train and my Y train. I'll take 2/3 of the data and then 1/3 of the data, and then I'll switch it and I'll do 3 different models so I can really see how well it tests out and how that averages out. This is the same thing but with the k-fold we're doing. and we're doing it across 20 sections. We'll go ahead and run this. And when we run this, it's not too exciting because we're just loading up the data and appending it into our list. And so what we want to take with this is we're going to go ahead and plot it. And this is where we can really see what's going on. This is where it gets exciting. So we take it and we're going to create a couple subplots. That way we have a nice setup down here. We're splitting it up into a couple different graphs. And let's go ahead and run this, and then we'll walk through it a little bit. So our subplot comes in. There's our subplot, and then our PLT plot we're going to do in there. Range 1, we're going to go ahead and do the splits +1 in PRA, list training error, ravel. This is, of course, just a code to how we properly set it up on there so that it sees it correctly. And then we have our X label, which is our number fold. Plot the Y label, training error. Plot the title, training error across folds. Plot the tight layout. Plot the subplot. So we're going to move on to, this is 1, 2, 1, 1, 2, 2. There's our just 1 and 2. It has to do with how it layers it on there for doing multiple plots, because you can do all kinds of cool things with our PyPlot library. And again, we're going to go ahead and do the same thing for the error. And we end up with our training error across folds and our testing error across folds. And so you can see these different folds, how they kind of spike and how they look. And so when we're talking about overfitting or underfitting, we're comparing these two graphs. And if one of them is more off than the other one, if you're looking at these two graphs, you got to say, hey, is this one overfit or underfit? And this is always a good question to ask. I mean, what do we got going here? Is that overfit or is that underfit? And I would say, based on these two graphs and the training data is more sporadic than the testing data. So I would look at this and say, hey, this might need to be fit a little bit better. Maybe we don't have enough data. With the iris, we probably don't. Something else is going on here. So it's a little underfit. Maybe a different model would fit better. I would not use a neural network model for this. I would actually use just a basic linear model on this. A lot of different choices. But this gives you an idea. What we're looking at is how chaotic are these two. Is it getting better or is it getting worse? If at some point the training data gets so much better than the testing data, you know you've overfit it. And that's where you start running into the overfitting. This to me looks like it's underfit. So that concludes underfitting and overfitting.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
Machine learning has improved our lives in a number of wonderful ways. Today, let's talk about some of these. I'm Rahul from Simplilearn, and these are the top 10 applications of machine learning. First, let's talk about virtual personal assistants. Google Assistant, Alexa, Cortana, and Siri. Now, we've all used one of these at least at some point in our lives. Now, these help improve our lives in a great number of ways. For example, you could tell them to call someone. You could tell them to play some music. You could tell them to even schedule an appointment. So how do these things actually work? First, they record whatever you're saying, send it over to a server, which is usually in a cloud, decode it with the help of machine learning and neural networks, and then provide you with an output. So if you've ever noticed that these systems don't work very well without the internet, that's because the server couldn't be contacted. Next, let's talk about traffic predictions. Now say I wanted to travel from Buckingham Palace to Lord's Cricket Ground. The first thing I would probably do is to get on Google Maps. So, search it. And let's put it here. So here we have the path you should take to get to Lord's Cricket Ground. Now here the map is a combination of red, yellow and blue. Now the blue regions signify a clear road, that is you won't encounter traffic there. The yellow indicate that they are slightly congested and red means they're heavily congested. So let's look at the map, a different version of the same map. And here, as I told you before, red means heavily congested, yellow means slow moving and blue means clear. So how exactly is Google able to tell you that the traffic is clear, slow moving, or heavily congested? So this is with the help of machine learning and with the help of two important measures. First is the average time that's taken on specific days at specific times on that route. The second one is the real-time location data of vehicles from Google Maps and with the help of sensors. Some of the other popular map services are Bing Maps, Maps.me, and here we go. Next up, we have social media personalization. So say I want to buy a drone and I'm on Amazon and I want to buy a DJI Mavic Pro. The thing is it's close to 1 lakh, so I don't want to buy it right now. But the next time I'm on Facebook, I'll see an advertisement for the product. Next time I'm on YouTube, I'll see an advertisement. Even on Instagram, I'll see an advertisement. So here, with the help of machine learning, Google has understood that I'm interested in this particular product. Hence, it's targeting me with these advertisements. This is also with the help of machine learning. Let's talk about email spam filtering. Now, this is the spam that's in my inbox. Now, how does Gmail know what's spam and what's not spam? So Gmail has an entire collection of emails which have already been labeled as spam or not spam. So after analyzing this data, Gmail is able to find some characteristics like the word lottery or winner. From then on, any new email that comes to your inbox goes through a few spam filters to decide whether it's spam or not. Now, some of the popular spam filters that Gmail uses is content filters, header filters, general blacklist filters, and so on. Next, we have online fraud detection. Now, there are several ways that online fraud can take place. For example, there's identity theft, where they steal your identity, fake accounts, where these accounts only last for how long the transaction takes place and stop existing after that, and man-in-the-middle attacks, where they steal your money while the transaction is taking place. The feed-forward neural network helps determine whether a transaction is genuine or fraudulent. So what happens with feed-forward neural networks are that the outputs are converted into hash values, and these values become the inputs for the next round. So for every real transaction that takes place, there's a specific pattern. A fraudulent transaction would stand out because of the significant changes that it would cause with the hash values. Stock market trading. Machine learning is used extensively when it comes to stock market trading. Now you have stock market indices like Nikkei. They use long short-term memory neural networks. Now these are used to classify, process, and predict data when there are time lags of unknown size and duration. Now this is used to predict stock market trends. Assistive medical technology. Now, medical technology has been innovated. With the help of machine learning, diagnosing diseases has been easier, from which we can create 3D models that can predict where exactly there are lesions in the brain. It works just as well for brain tumors and ischemic stroke lesions. They can also be used in fetal imaging and cardiac analysis. Now, some of the medical fields that machine learning will help assist in is disease identification, personalized treatment, drug discovery, clinical research, and radiology. And finally, we have automatic translation. Now, say you're in a foreign country and you see billboards and signs that you don't understand. That's where automatic translation comes of help. Now, how does automatic translation actually work? The technology behind it is the same as the sequence-to-sequence learning, which is the same thing that's used with chatbots. Here, the image recognition happens using convolutional neural networks, and the text is identified using optical character recognition. Furthermore, the sequence-to-sequence algorithm is also used to translate the text from one language to the other.
So first we will import some major libraries of Python. So here I will write import pandas as pd and import numpy as np. Then import cborn as sns. Okay. Then import sklearn dot model selection import train underscore test underscore split. Before that I will import matplotlib dot pyplot as plt. Okay, then I will write here from sklearn dot matrix import accuracy score. Then from sklearn dot matrix import classification to report. import re, then import string. Okay, then press enter. So it is saying, okay, here I have to write from. Everything seems good. Loading. Let's see. Okay, till then, NumPy is a Python library used for working with arrays. It also has function for working with the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for numerical Python. Pandas. So Panda is a software library written for Python programming language for data manipulation and analysis. In particular, it offers data structure and operation for manipulating numerical tables and time series. Then, Seaborn. An open source Python library based on Matplotlib is called Seaborn. It is utilized for data exploration and data visualization. With data frames and the Pandas library, Seaborn functions with ease. Then Matplotlib. For Python and its numerical extension NumPy, Matplotlib is a cross-platform for the data visualization and graphical charting package. As a result, it presents a strong open source suitable for MATLAB. The APIs for Matplotlib allow programmers to incorporate graphs into GUI applications. Then this train test split. We may build our training data and the test data with the aid of sklearn train test split function. This is so because the original dataset often serves as both the training data and the test data. Starting with a single dataset, we divide it into two datasets to obtain the information needed to create a model, like Hone and test. Accuracy score. The accuracy score is used to gauge the model's effectiveness by calculating the ratio of total true positive to total true negative across all the model prediction. This RE, regular expression. The functions in the model allow you to determine whether a given text fits a given regular expression or not, which is known as RE. Okay, then string. A collection of letters, words, or other characters is called a string. It is one of the basic data structure that serves as the foundation of manipulating data. The str class is a built-in string class in Python. Because Python strings are immutable, they cannot be modified after they have been formed. Okay, so now let's import the dataset. We will be going to import two datasets, one for the fake news and one for the true news, or you can say not fake news. Okay, so I will write here ef underscore fake equals to pd dot read underscore csv, or what can I say, df fake. Okay, data underscore fake. Okay, then fake dot csv. You can download this dataset from the description box below. Then data dot true equals to pd dot read underscore csv. Sorry, csv. Then fake news. Sorry, true. True dot csv. Okay. Then press enter. So these are the two datasets. You can download these datasets from the description box below. So let's see the board dataset. Okay. Then I will write here data underscore fake dot head. So this is the fake data. Okay. Then data underscore true dot head. And this is the true data. Okay. This is not fake. So if you want to see your top 5 rows of the particular dataset, you can use head. And if you want to see the last 5 rows of the dataset, you can use tail instead of head. Okay. So let me give some space for the better visual. So now we will insert column class as a target feature. Okay. Then I will write here data underscore fake class equals to 0. Then data underscore true and class equals to 1. Okay. Then I will write here data underscore fake dot shape and data underscore true dot shape. Okay. Then press enter. So the shape method returns the shape of an array. The shape is a tuple of integers. These numbers represent the length of the corresponding array dimension. In other words, a tuple containing the quantities of entries on each axis is an array shape dimension. So what's the meaning of shape? In the fake world, in this dataset, we have 2, 3, 4, 8, 1 rows and 5 columns. And in this dataset true, we have 2, 1, 4, 1, 7 rows and 5 columns. Okay, so these are the rows, column for the particular dataset. So now let's move and let's remove the last 10 rows for the manual testing. Okay, then I will write here data underscore fake underscore manual testing equals to data underscore fake dot tail. For the last 10 rows, I have to write here 10. Okay, so for I in range 2, 3, 4, 8, 1, sorry 0, comma 2, 3, 4, 7, 0, comma -1. Okay, then df underscore not df data underscore fake dot drop 1. Yeah, instead of 1 I can write here I comma axis equals to 0 in place equals to true. Then data not here data underscore same I will copy from here and I will paste it here and I will make the particular changes. So here I can write true, here I can write true. Okay, then I have to change a number 2 1 4 1 6. Write 2 1 4 0 6 -1. Same. So press enter. X is equals to 0. Let syntax. Maybe you mean 00 or show of this. Okay, we will put here double equals. And I'm putting this. Fake dot drop I x is equal to 0. अच्छा, in place. Okay. Here also write equals to and equals to. Yeah. So okay, axis is not defined. Now it's working. So let me see now. Data underscore fake dot shape. Okay, and data dot true and data underscore true dot shape. As you can see, 10 rows are deleted from each dataset. Yeah. So I will write here data underscore fake underscore manual testing class equals to 0 and data underscore true underscore manual underscore testing class equals to 1. Okay. Just ignore this warning. And let's see data underscore fake underscore manual testing dot head. As you can see, we have this, and then data dot underscore true underscore manual testing dot head. Done. Okay. This is the true data set. So here I will merge data underscore merge equals to pd dot concat. Concat is used for the concatenation. Data underscore fake data underscore true comma axis equals to 0. Then data underscore merge dot head the top 10 rows. Yeah, as you can see, the data is merged here. Okay. First it will come for the fake news and then with the for the true news. And let's merge true and fake data frames. Okay, we did this, and let's merge the column. Then data dot merge dot columns, or let's see the columns. It is not defined, but I did data underscore merge. These are the columns name, title, text, subject, date, class. Okay, now let's remove those columns which are not required for the further process. So here I will write data underscore or equals to data underscore merge crop title we don't need, then subject we don't need, then to 1. So let's check some null values. It's giving error. Where? Because of this. That's good. Then data dot is null dot sum. Center. So no null values. Okay. Then let's do the random shuffling of the data frames. Okay. For that, we have to write here data equals to data dot sample 1. Then data, okay, data dot hat. Okay. Now you can see here the random shuffling is done, and 1 for the true data set and 0 for the fake news one. Okay. Then let me write here data dot reset underscore index place equals to true. Data dot drop comma axis equals to 1, then comma in place equals to true. Okay. Then let me see columns now. Data dot columns. So here we have 2 columns only, rest we have deleted. Okay. So let me see data dot add. Yeah, everything seems good. Let's proceed further and let's create a function to process the text. Okay. For that, I will write here but okay, you can use any name text, and text equals to text dot lower. Okay. And text equals to re dot for the substring remove these things from the datas. Okay. So for that I'm writing here comma okay, then text equals to re dot substring comma comma text. Okay. Then I have to write text equals to re dot substring www dot s plus comma comma text. Okay, then text equals to re dot substring, then oh, comma, okay, then text equals to re dot substring, then percentage as again percentage for re dot escape function, right here string dot punctuation, okay, comma, then text, right? Then text equals to re dot substring and n comma text equals to re dot substring, right here, and again d, then again, okay, then comma, then again text here, okay, then at the end I have to write here return text. So everything like this these type of special character will be removed from the data set. Okay, let's run this. Let's see. Yeah, so here I will write df, sorry, not df, data, then text equals to data, okay, dot apply to the function name word opt, okay, and press enter. Yeah, so now let's define the dependent and independent variables. Okay, x equals to data text and y equals to data class. Okay, then splitting training and testing data. Okay, sorry. So here I will write x underscore train, comma x underscore test, then y underscore train, comma y underscore test equals to train underscore test underscore split, then x comma y comma test underscore size equals to 0.25. Okay, press enter. So now let's convert text to vectors. For that I have to write here let me z it's x. So here I will write from sklearn dot feature extraction dot text import t vectorizer. Okay, then vectorization equals to tfid vectorizer Okay, then xv underscore train equals to vectorization or ZATION vectorization dot fit, then transform x underscore train. Okay, then xv underscore test equals to vectorization dot transform x underscore test. Okay, then press enter. Uh, so now let's see our first model, logistic regression. So here I will write from sklearn dot linear underscore model. Okay, import logistic regression. Okay. Then lr equals to logistic regression, and I have to write here lr dot fit, then xv dot not dot xv dot train comma xv underscore test. Okay, press enter. lr dot xv dot train. Okay, here I have to write y train. Okay, then press enter. Will work. So here I will write prediction underscore linear regression equals to lr dot predict xv underscore test. Okay, let's see the accuracy score. For that I have to write lr dot score, then xv underscore test comma y underscore test. Okay, let's see the accuracy. So here as you can see, accuracy is quite good, 98%. Okay, now let's print the classification port y underscore test comma prediction of linear regression. Okay, so this is, you can see, precision score, then f1 score, then support value, accuracy. Okay, so now we will do this same for the decision tree, gradient boosting classifier, random forest classifier. Okay, then we will do model testing, then we will predict the score. Okay, so now for the decision tree classification. So for that I have to import from sklearn dot tree import decision tree classifier. Okay, then at the short form I will write here, I will copy it from here, then okay, then I have to write the same as this, so I will copy it from here and here. Just change linear regression to decision tree classifier. Okay, then I will write here same. So dt equals to dt dot predict xv underscore test. It's v still loading. It will take time. Okay, till then let me write here for the accuracy dt dot score v underscore test comma y. Okay, let's wait. Okay, let's run the accuracy. So as you can see, accuracy is good than this linear regression. Okay, logistic regression. Yeah, so let me show you the, let me predict print. Okay, so this is the accuracy score. This is the all the report. Yeah. So now let's move for the gradient boosting classifier. Okay, for that I have write from sklearn dot ensemble port gradient boosting classifier. Classifier. I will write here GB equals to, let me copy it from here. Okay. I will give here random underscore state equals to 0. Wait. So I will write here GB dot fit xv underscore train comma y underscore train. Okay, then press enter. Here I will write predict underscore GB equals to GB dot fit, sorry, predict xv dot test, not dot underscore test. Till then it's loading, so I will write here it's for the score. Then I will add GB dot score, then xv underscore test comma y underscore test. Okay, so let's wait. It is running this part. Till then let me write for the printing this. Okay, it's taking time. Still taking time. What if I will run this? It's not coming because of this. Yeah, it's done now. So you can see the accuracy is not good than decision tree, but yeah, it is also good, 99.4 something. Okay, so now let's check for the last one, random forest. First I will do, for the random forest we have to write from sklearn dot ensemble import random forest classifier. Okay. And here I will write RF equals to, right, I will copy it from here. Then random state equals to 0. Then RF dot fit v underscore train comma y underscore train. Okay, then press enter and predict underscore RC or F equals to RF dot predict v underscore test. Okay, till then I will write here, it's still loading, it will take time. So till then I will write for the score accuracy score xv underscore test comma y underscore test. Okay, then I will write here till then print classification port and y underscore test comma it will take time, little bit. So it run, the accuracy score is 99. It is also good. So now I will write the code for the model testing. So I will get back to you but after writing the code. So I have made two functions, one for the output label and one for the manual testing. Okay, so it will predict the all models from the repeat. So it will predict the news is fake or not from all the models. Okay, so for that let me write here news was to string put. Okay, then I will write here manual underscore testing. Okay. So here I will, you can add any news from the, you can copy it from the internet or whatever, from wherever you want. So I'm just copying from the internet. Okay, from the Google, the news which is not fake. Okay, I'm adding which is not fake because I already know, I searched on Google. So I'm entering this. So just run it, let's see what is showing. Okay, string input object is not callable. Okay, let me check this first. Okay, I have to give here str only. Yeah, let's check. Okay, I have to add here again the script. Yeah, the manual testing is not defined. Let me see manual testing. Okay, I have to edit something. It is just GB and it is just RF. Still GBC is not defined. Okay, okay. So what I have to do? I have to remove this. Okay. Everything seems sorted now. as I said to you, I just copied this news from the internet. I already know the news is not fake, so it is showing not a fake news. Okay, so now what I will do, I will copy one fake news from the internet, and let's see it is detecting it or not. Okay, so let me run this, and let me add the news for this. So all the models are predicting right it is a fake news, or you can add your own script like this is the fake news. Okay, I hope you guys understand till here. So I hope you guys must have understand how to detect a fake news using machine learning. You can copy any news from the internet and you can check it is fake or not. Okay, or if your model is predicting right or not.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
OpenCV, Open Source Computer Vision Library, is an open source computer vision and machine learning software library. It is written in C++ but has a binding for various programming languages such as Python, Java, MATLAB. OpenCV was designed with the goal of providing a common infrastructure for computer vision applications and to accelerate the use of machine learning perception in commercial product. OpenCV is widely used in a variety of industries, including robotics, automotive, and healthcare. It's supported by a large community of developers, researchers, and users who contribute to its development and provide support to its users. It is supported by a large community of developers, researchers, and users who contribute to its development and provide support to its users. So now let's see what is object detection. Object detection is a computer vision technology that involves identifying and localizing the object of interest within an image or a video. It is a challenging task as it involves not only recognizing the presence of an object but also detecting its precise location and size within the image or video. Object detection algorithm typically use deep learning techniques such as CNN to analyze the image or video for identifying the objects. These algorithms can also determine the boundaries of the object by drawing a bounding box around them. So after understanding what is object detection, now let's move on to the programming part. So this is a kernel, Python kernel. Here we will change this name. So here I will write object detection demo. Okay, so first we will import some major library like OpenCV. So for that we will write import cv2, and the next one is import matplotlib .pyplot as plt. So why we are writing plt? Because we can't write again and again matplotlib.pyplot. Okay, it's a long one, so we can write a short form plt. So yeah, so let's run this. So what is OpenCV? OpenCV is an open source software library for computer vision and machine learning. The OpenCV full form is Open Source Computer Vision Library. It was created to provide a shared infrastructure for application for computer vision and to speed up the use of machine learning perception in consumer products. OpenCV as a BSD licensed software make it simple for companies to use and change the code. Okay, so there are some predefined packages and libraries that make our life simple, and OpenCV is one of them. Second one is Matplotlib. Matplotlib is a easy to use and an amazing visualize library in Python. It is built on NumPy array and designed to work with broader SciPy stack and consists of several plots like line, bar, scatter, histogram, and many others. Okay, so moving forward, we will import our file. Okay, so here I will write config file equals to, this is our file name, ssd underscore mobilenet v3 large coco 22 14.bb. Okay, so you can find this
file on the description box below. Frozen model equals to, I'll explain you every single thing. Inference graph.pb. Okay, so let me run it first. MobileNet. As a name applied, the MobileNet model is designed to use in mobile application, and it's TensorFlow first mobile computer vision model. MobileNet used depth-wise separable convolutions. It significantly reduces the numbers of parameters when compared to the network with regular convolutions with the same depth in the nets. This results in the lightweight of the deep neural network. So MobileNet is a class of CNN that was open source by Google, and therefore this gives us an excellent starting point for training our classifiers that are insanely small and insanely fast. Okay, so what is this large COCO? This is a dataset, COCO dataset. Like with applications such as object detection, segmentation, and captioning, the COCO dataset is widely understood by the state-of-the-art of neural network. Its versatility and the multipurpose scene variations serve best to train a computer vision model and benchmark its performance. Okay, so what is COCO? The Common Object in Context is one of the most popular large-scale labeled images dataset available for public use. It represents a handful of objects we encounter on a daily basis and contains image annotations in 80 categories. I will show you the categories I have with over 1.5 million object instances. Okay, so modern day AI driven solutions are still not capable of producing absolute accuracy in result, which comes down to the fact that COCO dataset is a major benchmark for CV to train, test, and polish refined models for faster scaling of the annotation pipeline. On the top of that, the COCO dataset is a supplement to transfer learning, where the data used for one model serves as the starting point for the another. So what is frozen inference graph? Like freezing is the process to identify and save all the required graphs like weights and many others in a single file that you can easily use. A typical TensorFlow model contains 4 files, and this contains a complete graph. Okay, so forward, let's create one model. Here I will write model equals to cv2.dnn model frozen model and then config file. So here I am giving the parameters, 2 parameters like frozen model and config file. Let's go here. Yeah, we run it first. Okay, there is error, return error. Okay, so error is cv2.dnn detection model return as result with an exception set. The question comes, what is the meaning of detection model or DNN detection model? So this class represents a high-level API for object detection networks. Detection models allows to set parameters for pre-processing input image. Detection model creates net from file and with trained weights and config, sets its processing input, runs forward pass and return the result detections. Okay, moving forward, let's set the class labels. Okay, class labels. File name equals to labels.txt. I will put this file on the description box below. You can download from there. Open file name. Class labels. Strip. So here I created one array of name class labels. So this is the file name. What I'm doing, I'm putting this label file into this class labels. Okay, so here if I will print class labels, So these are the 80 categories in the COCO dataset. Okay, this person, bicycle, car, motorbike, aeroplane, bus, train, these all are the 80 categories. I will put this file label.txt in the description box below. You can download from there. Okay, fine. So let's print the length of the COCO dataset, or you can see class labels. This is 80. As you can see, I have already told you the length will be 80. So here let's set this some model input size, scaling, mean, and all. So I will write here model dot set input size 320 comma 320. Model dot set input scale 1.0 / 127.5. Okay, I will explain you, don't worry. Model dot set input mean 127.5 comma 127.5 comma 127.5. Okay, and then model dot set input swap b will be, what is set input size? Okay, so set input size is a size of new frame, the shape of the new blob less than 0. Okay, so this is the size of the new frame. The second one is set input scale. So set input scale is a scale factor of the value for the frame, or you can say the parameter will be the multiplier of the frame values, or you can say multiplier for the frame values. Okay, so set input mean, so it set the mean value for the frame in which the photo will come, the video will come, or my webcam will come. So it set the mean value for the frame, or the for parameters mean is scalar with the mean values which are subtracted from the channels, you can say. And the last one is set input swap RB. So it set the flag swap RB for the every frame. We don't have to put every time a single frame for a particular image. It will be set the true for the all the images. Okay, so parameters will be swap RB flag, which indicates the swap first and the last channels. So moving forward, we will import one image. Read boy.jpg dot I am show. So this is the size of 320 by 320. Okay, so first thing is you can download the random picture from the Google. I took from Google itself. So now what we will do, we will set the class index, the confidence value, the B box. B box is the boundary box which I will create for that particular person, cycle, motorbike, and the car. Okay, B equals to model get the confidence threshold. Threshold is used for if my model will confirm it's the particular image which is detecting is correct, it will print the name. Okay, so let me print class index is coming 1 2 3 4. Okay, so 1 means person, 2 means bicycle, 3 means car, and 4 means motorbike. This is the class index for particular label. What I will do, I will print the boxes font scale equals to 3 and the font equals to cv2 dot font Hershey plain for class index and the confidence and the boxes and x dot pattern confidence pattern box, the boundary box. Okay, then I will write here cv2 dot rectangle to make the rectangle, set the image and the boxes 5 comma 0 comma 0. This is the color of the box and this will be the thickness. Okay, then I will write cv2 dot put text image, then class labels. I will write class index -1 because always index start with 0, that's why, and the boxes 0 and comma boxes 1 body. Okay, font comma scale so font scale color equals to, this will be the text color 0 comma 255 comma 0 and the thickness so 3. Let me run it. No error. Okay, now plt dot I am show, then cv2 dot cvt color, then comma cvt2 dot color, then bgr to brg. That is why we wrote swap rb equals to true, because every time we will convert bgr to brg, sorry, rgb, so we don't have to write again and again. It will convert all the files into rgb. Okay, run it. Okay, as you can see, the motorbike is coming, bicycle is coming, the person is coming, the car will come, the car is coming. Okay, so it's detecting the right for the image. Now we will do this for the video and for the webcam. We are done with this image one, and then now I will write here. Okay, so this is will do for the video. For the video, I will write here cap equals to capture. You can write any name. So cv2 dot video capture. So you can take any random video. I took this pixels George. You can comment down. share the link before. App dot is open. So here I will write cap equals to CV2 dot video capture 0, and if not cap dot is open, then raise output error can't open the video. Can't open the video. Here everything will be the same. Font scale equals to 3. Okay, font equals to CV2 dot font Hershey 10. Okay, so here I will write while true comma frame equals to cap dot read. This is for the reading of the file. The same I will write class index comma confidence comma boundary box equals to model dot detect flame and the confidence threshold equals to 0.55. Okay, everything is the same we did before. So here I will print class index. Okay, so here I will write if and of the class index does not equals to 0, and what to perform is here after that for class index comma confidence comma boxes in zip class index dot flatten is a layers. Okay, confidence dot flatten box, and if class index is greater than equals to 80, then what to do? Then I will copy from here okay, the same thing I have to write here. So here I will write CV2 dot I am sure this will be the written in the frame object detection by Simplilearn and frame. So if CV2 dot wait key to and 0 the ffx equals to ordq. Okay, then here I will write break. Will you break when it gets into 2? The wait key will be 2. Okay, I will tell you what is the wait key. So here I will write cap dot release and cv2 dot destroy all windows. Okay, so now let me run. Let's see error. There will be error. Okay, CV Python programming language modules. Let me run it again. Are the wait keys. Okay, so video is here. The video is here. As you can see bicycle, the person, the bus, car, traffic light, the person. So our object detection for the video is coming right. Okay, person, okay, person, traffic light, bus. So this is how you can do for the video. Okay, so now we will do for the webcam live. So this is for the video. So if we want to do for the webcam, okay, so we need to just change one thing only. We have to change. Instead of giving the file, we have to write one here. Okay, the rest will be the same. Got it? So I have to just shut down my webcam. So let me shut down the webcam and get back to you. So as you can see, this is a 320 by 320 box. So this is coming right. Okay, so if I will show this, the mobile phone is coming right now. Okay, so this is how you can do the correct object detection.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
So first we will open command prompt to write a command to open Jupyter Notebook. So here we will write Jupyter Notebook. Then press enter. So it will take some time. Yeah. So this is the landing page of Jupyter Notebook, and here we have to new, then Python 3. So this is how the Jupyter Notebook UI look like. So at first we will import some major libraries of Python which help in creating a mass detection system. So here I will write import cv2, os, and press enter. Then I will give the path, then data path equals to c, then slash users, then slash slp 09375, then slash desktop, then slash, then face, mask detection, then slash dataset. Okay, so here it will be slash, my bad, sorry, and slash. Okay, it's look fine. So here I will write categories equals to os dot list directory, list dir. Then I will assign data underscore path. Then I will create some labels equals to here I will write here I for I in range. Then here I will give length of categories. Yeah. Then press enter. Then here I will write label. Then dict directory equals to directory. Then zip. Then categories comma labels. Yeah. So here I will write print. Then label directory. Okay. Then I will print categories. Then I will print labels. Okay, then press enter. Yeah. So here CV means capturing video. The CV2 function in OpenCV can read video capture by using pass 0. As a function parameter, we can access our webcam. We may pass RTSP URL in the function parameter to capture CCTV footage, which is quite helpful for video analysis. Then OS, this OS module. The OS module in Python has function for adding and deleting folders, retrieving their contents, changing the directory, locating the current directory, and more. Before you can communicate with the underlying operation system, you must import the OS module and this OS list directory to retrieve a list of all files and folders in the given directory. Use Python os.list directory method. The list of files or directory in the current working directory will be returned if no directory is specified. Then label. The tkinter widget class called a label is used to show text or an image. The user views the label, they cannot be interact with it. So moving forward, I will write code. So just stay with me. After that, I will explain you line wise. Okay. So here I will write that image underscore size equals to 100. Then I will create two classes, data, then target. Okay, arrays. Then I will write here for category in categories folder underscore path equals to os dot path then dot join then data underscore path comma category. Okay, then img image names equals to os dot list directory then folder path. Just stay with me, I will explain you line wise. Okay, so here I will write for img name in img names img underscore path equals to os dot path dot join. Then I will write here folder. I repeat. So here we will write folder underscore path, then img underscore name. So img equals to cv2 dot imread, then img underscore path. So here I will write try that gray equals to cv2 dot cvt, then capital C color, then img comma cv2 dot then color, then underscore bgr to rgb. Okay, so I will go for the gray one. CVT color bgr to rgb. Yeah, so I will write here resize. Okay, not in capital letter. Resize equals to cv2 dot resize, then gray comma img size comma img size. Why this 2 img size? Because like length and like width and breadth would be same, like 100. So press enter. So I will write data dot append, then resized, then target dot append, then label, then directory of category. Okay, so I will write here exception as E. So here I will print then exception comma E. Okay, then press enter. Let's see, there should be no error. So it is loading. Let's wait. Okay, no error. So image size should be like 100 by 100. So that is why I wrote here 100, then image size 100 by 100. And I made two arrays, like for one for data, then one for targets. So this for this gray equals to cvt.cvt color image. So converting the image into grayscale. Okay, then this line resize equals to cvt.resize gray img. So resizing the grayscale into like 100 by 100, since we need a fixed common size for all the images in the dataset. Okay, then this target dot append label directory. So appending the image like and the label categories into the list. What is list? Dataset. So like for the last print exception E. So if any exception raised, the exception will be printed here and the pass to the next image. Okay, so moving forward, let's import numpy and save this data and the target. Okay, so I will write here import numpy as np, right? Then I will write here data equals to np dot array, then again data by 255.0. Okay, then again data equals to np dot reshape, then data comma data dot shape, then 0 comma img size comma img size comma 1. Okay, then press enter. Then for target, let me do it just like this. Then target equals to np dot array, then target. Okay. So here I will write from keras dot utils import np utils. Okay, so here I will write new underscore target equals to np underscore utils dot to underscore categories, categorical, I guess, categorical, then target. Okay, then press enter. So here I will save np dot save this data comma data. Okay, and np dot save this target comma new target. Okay, so press enter. Yeah. So NumPy is a Python library used for working with arrays. It also has a function for working with in the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for Numerical Python and is Keras. A Python interface for artificial neural network is provided by the open source software package known as Keras. The TensorFlow library interface is provided by the Keras. A number of backends were supported by Keras up until version 2.3, including TensorFlow, Microsoft Cognitive. So this is the part of the data processing. This part of the data processing. So let me write here data preprocessing. So the data preprocessing part is done. Now we will create the another file of this Python for the training CNN. CNN means convolutional neural network. Okay, test data comma train underscore target comma test underscore target equals to train underscore split. Then we will split on data and target comma test size should be 0.1. Okay, so now I will give press enter. Okay, train split is not defined. Okay, it is train test split. Yeah. So now I will write checkpoint equals to model checkpoint, then again model I repeat. So here I will write model, comma, epoch, then 0 3D dot model. Okay. So here I will write comma monitor equals to value loss underscore loss comma verbose equals to 0 comma save best only equals to true comma mode equals to mode should be auto. Okay, then I will press enter. Then here I will write history equals to model dot fit to train underscore data comma okay train underscore target comma apochs equals to 20 comma callbacks equals to checkpoint comma validation underscore split equals to 0.2, the best ratio. Okay, so let me press enter. Okay, there is one error, model dot fit got an x. Okay, there should be a spelling mistake. epoch pochs equals to 20. Dot model, it is fine. Then monitor equals to value loss. Then verbose equals to 0. Save best only equals to true. Then mode. Okay, so here I have to write. Maybe it will. So it will take some time to go till 20. Okay, so it will download one by one. So we will wait for a while. So the model checkpoints are completed. So here I will write print, then model dot evaluate. Okay, here I will write test underscore data comma test underscore target. Then press enter. Okay, so I hope you guys understand till here. If you have any question or any query regarding any code, just put as in comments. Our team will shortly provide you the correct solution. Okay, so moving forward, we will create another file for detecting mask. Okay, so I will go here and then new file Python. So I will write here detecting mask file. Okay, yeah, so I will import some libraries here. Keras dot models import load models. We will import CV2 and we will import numpy as np. So press enter. Okay, numpy as np. Okay, so press enter. So what I will do, I will write here model equals to load underscore model, then okay, Keras model from Keras cannot import name. Okay, so it is model only. Yeah. So here I will add model equals to load model. So I will write here model 017 dot model. Okay. Okay, so here I will write face underscore classifier equals to cv2 dot cascade classifier. So this is one file for frontal face default. So you can find this file on the description box below. So I will write here her cascade underscore frontal face underscore default dot xml. Okay, so source equals to cv2 dot video capture 0. It will open our camera. So labels underscore directory equals to 0 mask and 1 for no mask. Okay, so color directory equals to like no mask for red and mask for green. Okay, so here at 0, then 0 comma 2 55 comma 0, then again comma for 1 there should be 0 comma 0 comma 255. Okay, so I hope you guys understand till here. So if you have any question or any query regarding any code, so just put as in comments. Our team will shortly provide you the correct solution. So the code is written. So let me run this. For this, first I have to first I have to close my this person on screen camera. So the code is running fine. Now it is showing no mask. Now it is showing mask. So I hope you guys understand till here. If you have any queries, any question regarding any code, just put as his comment. Our team will shortly provide you the correct solution.
If you are an aspiring machine learning engineer looking for online training and certifications from prestigious universities and in collaboration with leading experts, then search no more. Simplilearn's professional certification program in AI and machine learning from Purdue University in collaboration with IBM should be your right choice. For more details, use the link in the description box below with that in mind.
We'll talk about interview questions for machine learning. Now, this video will probably help you when you're attending interviews for machine learning positions, and the attempt here is to probably consolidate 30 most commonly asked questions and to help you in answering these questions. We tried our best to give you the best possible answers, but of course what is more important here is rather than the theoretical knowledge, you need to kind of add to the answers or supplement your answers with your own experience. So the responses that we put here are a bit more generic in nature, so that if there are some concepts that you are not clear, this video will help you in kind of getting those concepts cleared up as well. But what is more important is that you need to supplement these responses with your own practical experience. Okay, so with that, let's get started. So one of the first questions that you may face is, what are the different types of machine learning? Now, what is the best way to respond to this? There are three types of machine learning. If you read any material, you will always be told there are three types of machine learning. But what is important is you would probably be better off emphasizing that there are actually two main types of machine learning, which is supervised and unsupervised. And then there is a third type, which is reinforcement learning. So supervised learning is where you have some historical data and then you feed that data to your model to learn. Now, you need to be aware of a keyword that they will be looking for, which is labeled data. Right? So if you just say past data or historical data, the impact may not be so much. You need to emphasize on labeled data. So what is labeled data? Basically, let's say if you're trying to train your model for classification, you need to be aware of, for your existing data, which class each of the observations belong to, right? So that is what is labeling. So it is nothing but a fancy name, you must be already aware, but just make it a point to throw in that keyword labeled, so that will have the right impact. Okay, so that is what is supervised learning, when you have existing labeled data which you then use to train your model. That is known as supervised learning. And unsupervised learning is when you don't have this labeled data. So you have data, it is not labeled. So the system has to figure out a way to do some analysis on this. Okay, so that is unsupervised learning. And you can then add a few things like what are the ways of performing supervised learning and unsupervised learning, or what are some of the techniques. So supervised learning, we perform, or we do regression and classification, and unsupervised learning we do clustering. Okay? And clustering can be of different types. Similarly, regression can be of different types, but you don't have to probably elaborate so much. If they are asking for just the different types, you can just mention these and just at a very high level you can. But if they want you to elaborate, give examples, then of course I think there is a different question for that. We will see that later. Then the third, so we have supervised, then we have unsupervised, and then reinforcement. You need to provide a little bit of information around that as well, because it is sometimes a little difficult to come up with a good definition for reinforcement learning. So you may have to a little bit elaborate on how reinforcement learning works. Right? So reinforcement learning works in such a way that it basically has two parts to it. One is the agent and the environment, and the agent basically is working inside of this environment, and it is given a target that it has to achieve, and every time it is moving in the direction of the target, so the agent basically has to take some action, and every time it takes an action which is moving the agent towards the target, right, towards a goal. A target is nothing but a goal. Okay, then it is rewarded, and every time it is going in a direction where it is away from the goal, then it is punished. So that is the way you can a little bit explain, and this is used primarily, or very, very impactful for teaching the system to learn games and so on. Examples of this are basically used in AlphaGo. You can throw that as an example where AlphaGo used reinforcement learning to actually learn to play the game of Go, and finally it defeated the Go world champion. Right? This much of information that would be good enough. Okay. Then there could be a question on overfitting. So the question could be, what is overfitting and how can you avoid it? So what is overfitting? So let's first try to understand the concept, because sometimes overfitting may be a little difficult to understand. Overfitting is a situation where the model has kind of memorized the data. So this is an equivalent of memorizing the data. So we can draw an analogy so that it becomes easy to explain this. Now let's say you're teaching a child about recognizing some fruits or something like that. Okay, and you're teaching this child about recognizing, let's say, 3 fruits: apples, oranges, and pineapples. Okay, so this is a small child, and for the first time you're teaching the child to recognize fruits. Then, so what will happen? So this is very much like that is your training data set. So what you will do is you will take a basket of fruits which consists of apples, oranges, and pineapples. Okay, and you take this basket to this child, and there may be, let's say, hundreds of these fruits. So you take this basket to this child and keep showing each of this fruit, and then first time obviously the child will not know what it is. So you show an apple and you say, hey, this is apple. Then you show maybe an orange and say this is orange, and so on and so forth. And then again you keep repeating that, right? So till that basket is over. This is basically how training works in machine learning. Also, that's how training works. So till the basket is completed, maybe 100 fruits, you keep showing this child. And then in the process, what has happened, the child has pretty much memorized these. So even before you finish that basket, right, by the time you are halfway through, the child has learnt about recognizing the apple, orange, and pineapple. Now what will happen after halfway through? Initially you remember it made mistakes in recognizing, but halfway through now it has learned. So every time you show a fruit, it will exactly 100% accurately it will identify. It will say, the child will say this is an apple, this is an orange, and if you show a pineapple, it will say this is a pineapple. Right? So that means it has kind of memorized this data. Now let's say you bring another basket of fruits, and it will have a mix of maybe apples, which were already there in the previous set, but it will also have, in addition to apple, it will probably have a banana or maybe another fruit like a jackfruit. Right? So this is an equivalent of your test data set, which the child has not seen before. Some parts of it probably has seen, like the apples it has seen, but this banana and jackfruit it has not seen. So then what will happen? In the first round, which is an equivalent of your training data set, towards the end it has 100% it was telling you what the fruits are. Right? Apple was accurately recognized, orange was accurately recognized, and pineapples were accurately recognized. Right? So that is like 100% accuracy. But now when you get a fresh set which were not a part of the original one, what will happen? All the apples maybe it will be able to recognize correctly, but all the others like the jackfruit or the banana will not be recognized by the child. Right? So this is an analogy, this is an equivalent of overfitting. So what has happened during the training process, it is able to recognize or reach 100% accuracy, maybe very high accuracy. Okay, and we call that as very low loss. Right? So that is the technical term. So the loss is pretty much 0 and accuracy is pretty much 100%. Whereas when you use testing, there will be a huge error, which means the loss will be pretty high and therefore the accuracy will be also low. Okay, this is known as overfitting. This is basically a process where training is done. Training process it goes very well, almost reaching 100% accuracy, but while testing, it really drops down. Now, how can you avoid it? So that is the extension of this question. There are multiple ways of avoiding overfitting. There are techniques like what you call regularization. That is the most common technique that is used for avoiding overfitting. And within regularization, there can be a few other subtypes like dropout in case of neural networks and a few other examples. But I think if you give example or if you give regularization as the technique, probably that should be sufficient. So there will be some questions where the interviewer will try to test your fundamentals and your knowledge and depth of knowledge and so on and so forth. And then there will be some questions which are more like trick questions that will be more to stump you. Okay, then the next question is around the methodology. So when we are performing machine learning training, we split the data into training and test, right? So this question is around that. So the question is, what is training set and test set in machine learning model, and how is the split done? So the question can be like that. So in machine learning, when we are trying to train the model, so we have a 3-step process. We train the model and then we test the model, and then once we are satisfied with the test, only then we deploy the model. So what happens in the train and test is that you remember the labeled data. So let's say you have 1,000 records with labeling information. Now, one way of doing it is you use all the 1,000 records for training, and then maybe, right, which means that you have exposed all these 1,000 records during the training process, and then you take a small set of the same data and then you say, okay, I will test it with this. Okay, and then you probably, what will happen, you may get some good results. Right? But there is a flaw there. What is the flaw? This is very similar to human beings. It is like you are showing this model the entire data as a part of training. Okay, so obviously it has become familiar with the entire data. So when you're taking a part of that again and you're saying that I want to test it, obviously you will get good results. So that is not a very accurate way of testing. So that is the reason what we do is we have the label data of this 1,000 records or whatever. We set aside, before starting the training process, we set aside a portion of that data and we call that test set, and the remaining we call as training set, and we use only this for training our model. Now, the training process, remember, is not just about passing one round of this data set. So let's say now your training set has 800 records. It is not just one time you pass this 800 records. What you normally do is you actually, as a part of the training, you may pass this data through the model multiple times. So this 1,000 records may go through the model maybe 10, 15, 20 times till the training is perfect, till the accuracy is high, till the errors are minimized. Okay, now, so which is fine, which means that that is what is known as the model has seen your data and gets familiar with your data. And now when you bring your test data, what will happen is this is like some new data, because that is where the real test is. Now you have trained the model and now you are testing the model with some data which is kind of new. That is like a situation, like a realistic situation, because when the model is deployed, that is what will happen. It will receive some new data, not the data that it has already seen, right? So this is a realistic test. So you put some new data. So this data which you have set aside is for the model, it is new. And if it is able to accurately predict the values, that means your training has worked. Okay, the model got trained properly. But let's say while you're testing this with this test data, you're getting a lot of errors. That means you need to probably either change your model or retrain with more data and things like that. Now, coming back to the question of how do you split this, what should be the ratio? There is no fixed number. Again, this is like individual preferences. Some people split it into 50-50, 50% test and 50% training. Some people prefer to have a larger amount for training and a smaller amount for test. So they can go by either 60-40 or 70-30, or some people even go with some odd numbers like 65-35 or 63.33 and 33, which is like 1/3 and 2/3. So there is no fixed rule that it has to be something, the ratio has to be this. You can go by your individual preferences. Alright, then you may have questions around data handling, data manipulation, or what do you call data management or preparation. So these are all some questions around that area. There is again no one answer, one single good answer to this. It really varies from situation to situation, and depending on what exactly is the problem, what kind of data it is, how critical it is, what kind of data is missing, and what is the type of corruption. So there are a whole lot of things. This is a very generic question, and therefore you need to be a little careful about responding to this as well. So probably have to illustrate this again. If you have experience in doing this kind of work in handling data, you can illustrate with examples saying that I was on one project where I received this kind of data. These were the columns where data was not filled, or these were this many rows where the data was missing. That would be, in fact, a perfect way to respond to this question. But if you don't have that, obviously, you have to provide some good answer. I think it really depends on what exactly the situation is. And there are multiple ways of handling the missing data or corrupt data. Now, let's take a few examples. Now, let's say you have data where some values in some of the columns are missing, and you have pretty much half of your data having these missing values in terms of number of rows. Okay, that could be one situation. Another situation could be that you have records or data missing, but when you do some initial calculation, how many records are corrupt, or how many rows or observations, as we call it, has this missing data. Let's assume it is very minimal, like 10%. Okay. Now, between these two cases, how do we? So let's assume that this is not a mission critical situation, and in order to fix this 10% of the data, the effort that is required is much higher, and obviously effort means also time and money, right? So it is not so mission critical, and it is okay to, let's say, get rid of these records. So obviously one of the easiest ways of handling the data part or missing data is remove those records or remove those observations from your analysis. So that is the easiest way to do. But then the downside is, as I said, as in the first case, if let's say 50% of your data is like that, because some column or the other is missing. So it is not like in every place, in every row, the same column is missing, but you have in maybe 10% of the records, column 1 is missing, and another 10% column 2 is missing, another 10% column 3 is missing, and so on and so forth. So it adds up to maybe half of your data set. So you cannot completely remove half of your data set, then the whole purpose is lost. Okay, so then how do you handle? Then you need to come up with ways of filling up this data with some meaningful value, right? That is one way of handling. So when we say meaningful value, what is that meaningful value? Let's say for a particular column, you might want to take a mean value for that column and fill wherever the data is missing, fill up with that mean value, so that when you're doing the calculations, your analysis is not completely way off. So you have values which are not missing, first of all, so your system will work. Number two, these values are not so completely out of whack that your whole analysis goes for a toss. Right? There may be situations where if the missing values, instead of putting mean, maybe a good idea to fill it up with the minimum value or with a 0. So, or with a maximum value. Again, as I said, there are so many possibilities. So there is no like one correct answer for this. You need to basically talk around this and illustrate with your experience. As I said, that would be the best. Otherwise, this is how you need to handle this question. Okay, so then the next question can be, how can you choose a classifier based on a training set data size? So again, this is one of those questions where you probably do not have like a one-size-fits-all answer. First of all, you may not, let's say, decide your classifier based on the training set size. Maybe not the best way to decide the type of the classifier. And even if you have to, there are probably some thumb rules which we can use. But then again, every time, so in my opinion, the best way to respond to this question is you need to try out few classifiers irrespective of the size of the data, and you need to then decide on your particular situation which of these classifiers are the right ones. This is a very generic issue, so you will never be able to, just by if somebody defines a problem to you, and somebody, even if they show the data to you or tell you what is the data or even the size of the data, I don't think there is a way to really say that yes, this is the classifier that will work here. No, that's not the right way. So you need to still, test it out, get the data, try out a couple of classifiers, and then only you will be in a position to decide which classifier to use. You try out multiple classifiers, see which one gives the best accuracy, and only then you can decide. Then you can have a question around confusion matrix. So the question can be, explain confusion matrix. Right? So confusion matrix, I think the best way to explain it is by taking an example and drawing like a small diagram. Otherwise it can really become tricky. So my suggestion is to take a piece of pen and paper and explain it by drawing a small matrix. And confusion matrix is about to find out, this is used especially in classification learning process, and when you get the results, when our model predicts the results, you compare it with the actual value and try to find out what is the accuracy. Okay, so in this case, let's say this is an example of a confusion matrix, and it is a binary matrix. So you have the actual values, which is the labeled data, right? And which is, so you have how many yes and how many no. So you have that information, and you have the predicted values, how many yes and how many no, right? So the total actual values, the total yes is 12 plus 1, 13, and they are shown here. And the actual value no's are 9 plus 3, 12. Okay, so that is what this information here is. So this is about the actual, and this is about the predicted. Similarly, the predicted values, there are yes are 12 plus 3, 15 yeses, and no are 1 plus 9, 10 no's. Okay, so this is the way to look at this confusion matrix. Okay, and out of this, what is the meaning conveyed here? So there are 2 or 3 things that needs to be explained outright. The first thing is, for a model to be accurate, the values across the diagonal should be high, like in this case, right? That is one. Number 2, the total sum of these values is equal to the total observations in the test data set. So in this case, for example, you have 12 plus 3, 15 plus 10, 25. So that means we have 25 observations in our test data set. Okay, so these are the 2 things you need to first explain, that the total sum in this matrix, the numbers, is equal to the size of the test data set, and the diagonal values indicate the accuracy. So by looking at it, you can probably have an idea about, is this an accurate model? Is the model being accurate? If they're all spread out equally in all these 4 boxes, that means probably the accuracy is not very good. Okay. Now, how do you calculate the accuracy itself, right? How do you calculate the accuracy itself? So it is a very simple mathematical calculation. You take sum of the diagonals, right? So in this case, it is 9 plus 12, 21, and divide it by the total. So in this case, what will it be? Let me take a pen. So your diagonal values is equal to, if I say D is equal to 12 plus 9, so that is 21, right? And the total data set is equal to, right, we just calculated, it is 25. So what is your accuracy? It is 21 by, so your accuracy is equal to 21 by 25, and this turns out to be about 85%. Right, so this is 85%. So that is our accuracy. Okay, so this is the way you need to explain, draw a diagram, give an example, and maybe it may be a good idea to be prepared with an example so that it becomes easy for you. You don't have to calculate those numbers on the fly, right? So a couple of hints are that you take some numbers which add up to 100. That is always a good idea, so you don't have to really do this complex calculations. So the total value will be 100, and then diagonal values you divide. Once you find the diagonal values, that is equal to your percentage. Okay. All right. So the next question can be a related question about false positive and false negative. So what is false positive and what is false negative? Now, once again, the best way to explain this is using a piece of paper and pen. Otherwise, it will be pretty difficult to explain this. So we use the same example of the confusion matrix, and we can explain that. So a confusion matrix looks somewhat like this, and when we just take looks somewhat like this, and we continue with the previous example where this is the actual value, this is the predicted value, and in the actual value we have 12 plus 1 13 yeses and 3 plus 9 12 no's, and the predicted values, there are 12 plus 3 15 yeses and 1 plus 9 10 no's. Okay. Now, in this particular case, which is the false positive. What is a false positive? First of all, the second word, which is positive, okay, is referring to the predicted value. So that means the system has predicted it as a positive, but the real value, so this is what the false comes from, but the real value is not positive. Okay, that is the way you should understand this term, false positive or even false negative. So false positive, so positive is what your system has predicted. So where is that system predicted? This is the one. Positive is what? Yes. So you basically consider this row. Okay. Now if you consider this row, so this is all positive values. This entire row is positive values. Okay. Now the false positive is the one where the actual value is negative. Predicted value is positive, but the actual value is negative. So this is a false positive, right? And here is a true positive. So the predicted value is positive and the actual value is also positive. Okay, I hope this is making sense. Now let's take a look at what is false negative. False negative. So negative is the second term. That means that is the predicted value that we need to look for. So which are the predicted negative values? This row corresponds to predicted negative values. All right. So this row corresponds to predicted negative values. And what they are asking for? False. So this is the row for predicted negative values and the actual value is this one, right? This is predicted negative and the actual value is also negative. Therefore, this is a true negative. So the false negative is this one. Predicted is negative, but actual is positive, right? So this is the false negative. So this is the way to explain, and this is the way to look at false positive and false negative. Same way, there can be true positive and true negative as well. So again, positive, the second term you will need to use to identify the predicted row, right? So if we say true positive, positive we need to take for the predicted part. So predicted positive is here. Okay, and then the first term is for the actual. So true positive. So true in case of actual is yes, right? So true positive is this one. Okay, and then in case of actual, the negative. Now we are talking about, let's say, true negative. True negative. Negative is this one, and the true comes from here. So this is true negative, right? 9 is true negative. The actual value is also negative and the predicted value is also negative. Okay, so that is the way you need to explain this, the terms false positive, false negative, and true positive, true negative. Then you might have a question like, what are the steps involved in the machine learning process, or what are the 3 steps in the process of developing a machine learning model, right? So it is around the methodology that is applied. So basically, the way you can probably answer in your own words, but the way the model development of the machine learning model happens is like this. So first of all, you try to understand the problem and try to figure out whether it is a classification problem or a regression problem. Based on that, you select a few algorithms and then you start the process of training these models. Okay, so you can either do that, or you can, after due diligence, you can probably decide that there is one particular algorithm which is most suitable. Usually it happens through trial and error process, but at some point you will decide that, okay, this is the model we are going to use. Okay, so in that case, we have the model, algorithm, and the model decided, and then you need to do the process of training the model and testing the model. And this is where, if it is supervised learning, you split your data, the labeled data, into training data set and test data set. And you use the training data set to train your model. And then you use the test data set to check the accuracy, whether it is working fine or not. So you test the model before you actually put it into production, right? So once you test the model, you're satisfied it's working fine, then you go to the next level, which is putting it for production. And then in production, obviously new data will come and the inference happens. So the model is readily available, and only thing that happens is new data comes and the model predicts the values, whether it is regression or classification. Now, so this can be an iterative process. So it is not a straightforward process where you do the training, do the testing, and then you move it to production. No. So during the training and test process, there may be a situation where, because of either overfitting or things like that, the test doesn't go through, which means that you need to put that back into the training process. So that can be an iterative process. Not only that, even if the training and test goes through properly and you deploy the model in production, there can be a situation that the data that actually comes, the real data that comes, with that, this model is failing. So in which case you may have to once again go back to the drawing board. Or initially it will be working fine, but over a period of time, maybe due to the change in the nature of the data, once again the accuracy will deteriorate. So that is again a recursive process. So once in a while, you need to keep checking whether the model is working fine or not. And if required, you need to tweak it and modify it and so on and so forth. So net, this is a continuous process of tweaking the model and testing it and making sure it is up to date. Then you might have question around deep learning. So because deep learning is now associated with AI, artificial intelligence, and so on. So it can be as simple as, what is deep learning? So I think the best way to respond to this could be, deep learning is a part of machine learning. And then obviously the question would be, then what is the difference, right? So deep learning, you need to mention there are 2 key parts that interviewer will be looking for when you are defining deep learning. So first is, of course, deep learning is a subset of machine learning. So machine learning is still the bigger, let's say, scope, and deep learning is one part of it. So then what exactly is the difference? Deep learning is primarily when we are implementing these our algorithms, or when we are using neural neural networks for doing our training and classification and regression and all that, right? So when we use neural network, then it is considered as deep learning. And the term deep comes from the fact that you can have several layers of neural networks, and these are called deep neural networks, and therefore the term deep, deep learning. The other difference between machine learning and deep learning, which the interviewer may be wanting to hear, is that in case of machine learning, the feature engineering is done manually. What do we mean by feature engineering? Basically, when we are trying to train our model, we have our training data, right? So we have our training labeled data, and this data has several, let's say if it is a regular table, it has several columns. Now each of these columns actually has information about a feature, right? So if we are trying to predict height, weight, and so on and so forth, so these are all features of human beings. Let's say we have census data and we have all this. So those are the features. Now there may be probably 50 or 100, in some cases there may be 100 such features. Now all of them do not contribute to our model, right? So we as a data scientist, we have to decide whether we should take all of them, all the features, or we should throw away some of them, because again, if we take all of them, number one, of course, your accuracy will probably get affected, but also there is a computational part. So if you have so many features and then you have so much data, it becomes very tricky. So in case of machine learning, we manually take care of identifying the features that do not contribute to the learning process, and thereby we eliminate those features and so on, right? So this is known as feature engineering, and in machine learning we do that manually. Whereas in deep learning, where we use neural networks, the model will automatically determine which features to use and which to not use, and therefore feature engineering is also done automatically. So this is an explanation. These are two key things probably will add value to your response. All right, so the next question is, what is the difference between, or what are the differences between machine learning and deep learning? So here, this is a quick comparison table between machine learning and deep learning. And in machine learning enables machines to take decisions on their own based on past data. So here we are talking primarily of supervised learning. And it needs only a small amount of data for training, and then works well on low-end systems, so you don't need large machines. And most features need to be identified in advance and manually coded. So basically the feature engineering part is done manually, and the problem is divided into parts and solved individually and then combined. So that is about the machine learning part. In deep learning basically enables machines to take decisions with the help of artificial neural networks. So here in deep learning we use neural nets. So that is the key differentiator between machine learning and deep learning. And usually deep learning involves a large amount of data, and therefore the training also requires, usually the training process requires high-end machines because it needs a lot of computing power. And the machine learning features the feature engineering is done automatically. So the neural networks takes care of doing the feature engineering as well. And in case of deep learning, therefore, it is said that the problem is handled end to end. So this is a quick comparison between machine learning and deep learning in case you have that kind of a question. Then you might get a question around the uses of machine learning or some real life applications of machine learning in modern business. The question may be worded in different ways, but the meaning is how exactly is machine learning used, or actually supervised machine learning. It could be a very specific question around supervised machine learning. So this is like give examples of supervised machine learning, use of supervised machine learning in modern business. So that could be the next question. So there are quite a few examples or quite a few use cases, if you will, for supervised machine learning. The very common one is email spam detection. So you want to train your application or your system to detect between spam and non-spam. So this is a very common business application of supervised machine learning. So how does this work? The way it works is that you obviously have historical data of your emails, and they are categorized as spam and not spam. So that is what is the labeled information. And then you feed this information or all these emails as an input to your model, right? and the model will then get trained to detect which of the emails are to detect which is spam and which is not spam. So that is the training process, and this is supervised machine learning because you have labeled data. You already have emails which are tagged as spam or not spam, and then you use that to train your model, right? So this is one example. Now there are a few industry specific applications for supervised machine learning. One of the very common ones is in healthcare diagnostics. In healthcare diagnostics, you have these images and you want to train models to detect whether from a particular image, whether it can find out if the person is sick or not, whether a person has cancer or not. Right? So this is a very good example of supervised machine learning. Here, the way it works is that existing images, it could be X-ray images, it could be MRI or any of these images are available and they are tagged saying that, okay, this X-ray image is defective or the person has an illness, or it could be cancer, whichever illness, right? So it is tagged as defective or clear or good image and defective image, something like that. So we come up with a binary, or it could be multi-class as well, saying that this is defective to 10%, this is 25%, and so on. But let's keep it simple. You can give an example of just a binary classification, that would be good enough. So you can say that in healthcare diagnostics, using image, we need to detect whether a person is ill or whether a person is having cancer or not. So here, the way it works is you feed labeled images and you allow the model to learn from that, so that when new image is fed, it will be able to predict whether this person is having that illness or not, having cancer or not, right? So I think this would be a very good example for supervised machine learning in modern business. All right, then we can have a question like, so we've been talking about supervised and unsupervised, and so there can be a question around semi-supervised machine learning. So what is semi-supervised machine learning? Now, semi-supervised learning, as the name suggests, it falls between supervised learning and unsupervised learning, but for all practical purposes, it is considered as a part of supervised learning. And the reason this has come into existence is that in supervised learning, you need labeled data. So all your data for training your model has to be labeled. Now, this is a big problem in many industries or under many situations. Getting the labeled data is not that easy because there's a lot of effort in labeling this data. Let's take an example of the diagnostic images. We can just, let's say, take X-ray images. Now, there are actually millions of X-ray images available all over the world. But the problem is they are not labeled. So their images are there, but whether it is defective or whether it is good, that information is not available along with it, right, in a form that it can be used by a machine, which means that somebody has to take a look at these images, and usually it should be like a doctor, and then say that, okay, yes, this image is clean and this image is cancerous, and so on and so forth. Now, that is a huge effort by itself. So this is where semi-supervised learning comes into play. So what happens is there is a large amount of data. Maybe a part of it is labeled. Then we try some techniques to label the remaining part of the data so that we get completely labeled data, and then we train our model. So I know this is a little long winding explanation, but unfortunately there is no quick and easy definition for semi-supervised machine learning. This is the only way probably to explain this concept. We may have another question as what are unsupervised machine learning techniques, or what are some of the techniques used for performing unsupervised machine learning? So it can be worded in different ways. So how do we answer this question? So unsupervised learning, you can say that there are two types, clustering and association. And clustering is a technique where similar objects are put together. And there are different ways of finding similar objects. So their characteristics can be measured, and if they have, in most of the characteristics, if they are similar, then they can be put together. This is clustering. Then association, I think the best way to explain association is with an example. In case of association, you try to find out how the items are linked to each other. So for example, if somebody bought maybe a laptop, the person has also purchased a mouse. So this is more in an e-commerce scenario, for example. So you can give this as an example. So people who are buying laptops are also buying the mouse. So that means there is an association between laptops and mouse. Or maybe people who are buying bread are also buying butter. So that is a association that can be created. So this is unsupervised learning, one of the techniques. Okay. All right, then we have very fundamental question. What is the difference between supervised and unsupervised machine learning? So machine learning, these are the two main types of machine learning, supervised and unsupervised. And in case of supervised, and again here, probably the keyword that the person may be wanting to hear is labeled data. Now, very often people say, we have historical data, and if we run it, it is supervised, and if we don't have historical data, yes, but you may have historical data, but if it is not labeled, then you cannot use it for supervised learning. So it's very key to understand that we put in that keyword labeled. Okay. So when we have labeled data for training our model, then we can use supervised learning. And if we do not have labeled data, then we use unsupervised learning. And there are different algorithms available to perform both of these types of trainings. So there can be another question, a little bit more theoretical and conceptual in nature. This is about inductive machine learning and deductive machine learning. So the question can be, what is the difference between inductive machine learning and deductive machine learning, or somewhat in that manner, so that the exact phrase or exact question can vary. They can ask for examples and things like that, but that could be the question. So let's first understand what is inductive and deductive training. Inductive training is induced by somebody, and you can illustrate that with a small example. I think that always helps. So whenever you're doing some explanation, try as much as possible, as I said, to give examples from your work experience or give some analogies, and that will also help a lot in explaining as well, and for the interviewer also to understand. So here we'll take an example, or rather we will use an analogy. So inductive training is when we induce some knowledge or the learning process into a person without the person actually experiencing it. Okay, what can be an example? So we can probably tell the person or show a person a video that fire can burn his finger, or fire can cause damage. So what is happening here? This person has never probably seen a fire or never seen anything getting damaged by fire. But just because he has seen this video, he knows that, okay, fire is dangerous, and if fire can cause damage. Right? So this is inductive learning. Compared to that, what is deductive learning? So here you draw conclusion, or the person draws conclusion out of experience. So we will stick to the analogy. So compared to the showing a video, let's assume a person is allowed to play with fire. Right? And then he figures out that if he puts his finger, it's burning, or if he throws something into the fire, it burns. So he is learning through experience. So this is known as deductive learning. Okay, so you can have applications or models that can be trained using inductive learning or deductive learning. All right, I think probably that explanation will be sufficient. The next question is, are KNN and K-means clustering similar to one another, or are they same? Right, because the letter K is kind of common between them. Okay, so let us take a little while to understand what these two are. One is KNN, another is K-means. KNN stands for K nearest neighbors, and K means, of course, is the clustering mechanism. Now, these two are completely different, except for the letter K being common between them. KNN is completely different. K means clustering is completely different. KNN is a classification process, and therefore it comes under supervised learning, whereas K-means clustering is actually unsupervised. Okay, when you have KNN, when you want to implement KNN, which is basically K nearest neighbors, the value of K is a number. So you can say K is equal to 3. You want to implement KNN with K is equal to 3. So which means that it performs the classification in such a way that, how does it perform the classification? So it will take 3 nearest objects, and that's why it's called nearest neighbor. So basically based on the distance, it will try to find out its nearest objects that are, let's say, 3 of the nearest objects, and then it will check whether the class they belong to which class, right? So if all three belong to one particular class, obviously this new object is also classified as that particular class. But it is possible that they may be from 2 or 3 different classes. Okay, so let's say they are from 2 classes, and then if they are from 2 classes, now usually you take a odd number, you assign an odd number to. So if there are 3 of them and 2 of them belong to one class and then 1 belongs to another class, so this new object is assigned to the class to which the 2 of them belong. Now, the value of k is sometimes tricky. Whether should you use 3, should you use 5, should you use 7? That can be tricky because the ultimate classification can also vary. So it's possible that if you're taking k as 3, the object is probably in one particular class, but if you take k is equal to 5, maybe the object will belong to a different class, because when you're taking 3 of them, probably 2 of them belong to class 1 and 1 belong to class 2. Whereas when you take 5 of them, it is possible that only 2 of them belong to class 1 and 3 of them belong to class 2. So which means that this object will belong to class 2, right? So you see that? So the class allocation can vary depending on the value of k. Now, k-means on the other hand is a clustering process, and it is unsupervised, where what it does is the system will basically identify how the objects are, how close the objects are with respect to some of their features. Okay, but the similarity of course is the letter k, and in case of k-means also we specify its value, and it could be 3 or 5 or 7. There is no technical limit as such, but it can be any number of clusters that you can create. Okay, so based on the value that you provide, the system will create that many clusters of similar objects. So there is a similarity to that extent that k is a number in both the cases, but actually these two are completely different processes. We have what is known as naive Bayes classifier, and people often get confused thinking that naive Bayes is the name of the person who found this classifier or who developed this classifier, which is not 100% true. Bayes is the name of the person, B-A-Y-E-S is the name of the person, but naive is not the name of the person, right? So naive is basically an English word, and that has been added here because of the nature of this particular classifier. Naive Bayes classifier is a probability based classifier, and it makes some assumptions that presence of one feature of a class is not related to the presence of any other feature of maybe other classes, right? So which is not a very strong or not a very, accurate assumption, because these features can be related and so on. But even if we go with this assumption, this whole algorithm works very well even with this assumption, and that is the good side of it. But the term comes from there, so that is the explanation that you can give. Then there can be question around reinforcement learning. It can be paraphrased in multiple ways. One could be, can you explain how a system can play a game of chess using reinforcement learning? Or it can be any game. So the best way to explain this is again to talk a little bit about what reinforcement learning is about, and then elaborate on that to explain the process. So first of all, reinforcement learning has an environment and an agent, and the agent is basically performing some actions in order to achieve a certain goal. And these goals can be anything, either if it is related to game, then the goal could be that you have to score very high, score a high value, high number. Or it could be that your number of lives should be as high as possible. Don't lose lives. So these could be some of them. More advanced examples could be for driving. In the automotive industry, self-driving cars, they actually also make use of reinforcement learning to teach the car how to navigate through the roads and so on and so forth. That is also another example. Now, how does it work? So if the system is basically there is an agent and environment, and every time the agent takes a step or performs a task which is taking it towards the goal, the final goal, let's say to maximize the score or to minimize the number of lives and so on, or minimize the deaths, for example, it is rewarded. And every time it takes a step which goes against that goal, right, contrary or in the reverse direction, it is penalized. Okay, so it is like a carrot and stick system. Now, how do you use this to create a game of chess, or to create a system to play a game of chess? Now, the way this works is, and this could probably go back to this AlphaGo example where AlphaGo defeated a human champion. So the way it works is in reinforcement learning, the system is allowed, for example, if in this case we are talking about chess, so we allow the system to first of all watch playing a game of chess. So it could be with a human being or it could be the system itself. There are computer games of chess, right? So either this new learning system has to watch that game or watch a human being play the game, because this is reinforcement learning is pretty much all visual. So when you're teaching the system to play a game, the system will not actually go behind the scenes to understand the logic of your software, of this game or anything like that. It is just visually watching the screen and then it learns. Okay, so reinforcement learning to a large extent works on that. So you need to create a mechanism whereby your model will be able to watch somebody playing the game, and then you allow the system also to start playing the game. So it pretty much starts from scratch. Okay. And as it moves forward, it's right at the beginning, the system really knows nothing about the game of chess. Okay, so initially it is a clean slate. It just starts by observing how you're playing. So it will make some random moves and keep losing badly. But then what happens is over a period of time, so you need to now allow the system, or you need to play with the system, not just 1, 2, 3, 4 or 5 times, but hundreds of times, thousands of times, maybe even hundreds of thousands of times. And that's exactly how AlphaGo has done. It played millions of games between itself and the system, right? So for the game of chess also, you need to do something like that. You need to allow the system to play chess and then learn on its own over a period of repetition. So I think you can probably explain it to this much, to this extent, and it should be sufficient. Now, this is another question which is again somewhat similar, but here the size is not coming into picture. So the question is, how will you know which machine learning algorithm to choose for your classification problem? Now, this is not only classification problem, it could be a regression problem. I would like to generalize this question. So if somebody asks you, how will you choose? How will you know which algorithm to use? The simple answer is there is no way you can decide exactly saying that this is the algorithm I'm going to use. In a variety of situations, there are some guidelines. Like for example, you will obviously, depending on the problem, you can say whether it is a classification problem or a regression problem. And then in that sense, you are kind of restricting yourself to, if it is a classification problem, you can only apply a classification algorithm, right? To that extent, you can probably, let's say, limit the number of algorithms. But now within the classification algorithms, you have decision trees, you have SVM, you have logistic regression. Is it possible to outright say, yes, so for this particular problem, since you have explained this, now this is the exact algorithm that you can use? That is not possible. Okay, so we have to try out a bunch of algorithms, see which one gives us the best performance and best accuracy, and then decide to go with that particular algorithm. So in machine learning, a lot of it happens through trial and error. There is no real possibility that anybody can, just by looking at the problem or understanding the problem, tell you that, okay, in this particular situation, this is exactly the algorithm that you should use. Then the questions may be around application of machine learning, and this question is specifically around how Amazon is able to recommend other things to buy. So this is around recommendation engine. How does it work? How does the recommendation engine work? So this is basically the question is all about. So the recommendation engine again works based on various inputs that are provided. Obviously something like Amazon, a website or e-commerce site like Amazon collects a lot of data around the customer behavior, who is purchasing what. And if somebody is buying a particular thing, they're also buying something else. So this kind of association, right? So this is the unsupervised learning we talked about. They use this to associate and link or relate items. And that is one part of it. So they kind of build association between items, saying that somebody buying this is also buying this. That is one part of it. Then they also profile the users, right? Based on their age, their gender, their geographic location. They will do some profiling. And then when somebody is logging in and when somebody is shopping, kind of the mapping of these two things are done. They try to identify, obviously, if you have logged in, then they know who you are and your information is available. Like, for example, your age, maybe your gender, and where you're located, what you purchased earlier. Right? So all this is taken, and the recommendation engine basically uses all this information and comes up with recommendations for a particular user. So that is how the recommendation engine works. Alright, then the question can be something very basic, like when will you go for classification versus regression, right? When do you do classification instead of regression, or when will you use classification instead of regression? Now, yes, so this is basically going back to the understanding of the basics of classification and regression. So classification is used when you have to identify or categorize things into discrete classes. So the best way to respond to this question is to take up some examples and use it. Otherwise, it can become a little tricky. The question may sound very simple, but explaining it can sometimes be very tricky. In case of regression, we use, of course, there will be some keywords that they will be looking for. So just you need to make sure you use those keywords. One is the discrete values, another is the continuous values. So for regression, if we are trying to find some continuous values, you use regression. Whereas if you're trying to find some discrete values, you use classification. And then you need to illustrate. What are some of the examples? So classification is like, let's say there are images and you need to put them into classes like cat, dog, elephant, tiger, something like that. So that is a classification problem. Or it can be, that is a multi-class classification problem. It could be binary classification problem, like for example, whether a customer will buy or he will not buy. That is a classification, binary classification. It can be in the weather forecast area. Now, weather forecast is again combination of regression and classification, because on the one hand, you want to predict whether it's going to rain or not. That's a classification problem. That's a binary classification, right? Whether it's going to rain or not rain. However, you also have to predict what is going to be the temperature tomorrow, right? Now, temperature is a continuous value. You can't answer the temperature in a yes or no kind of a response, right? So what will be the temperature tomorrow? So you need to give a number, which can be like 20 degrees, 30 degrees or whatever. Right? So that is where you use regression. One more example is stock price prediction. So that is where again you will use regression. So these are the various examples. So you need to illustrate with examples and make sure you include those keywords like discrete and continuous. So the next question is more about a little bit of a design related question to understand your concepts and things like that. So it is, how will you design a spam filter? So how do you basically design or develop a spam filter? So I think the main thing here is he is looking at probably understanding your concepts in terms of what is the algorithm you will use, or what is your understanding about difference between classification and regression and things like that, right? And the process, of course, the methodology and the process. So the best way to go about responding to this is we say that, okay, this is a classification problem because we want to find out whether an email is a spam or not spam, so that we can apply the filter accordingly. So first thing is to identify what type of a problem it is. So we have identified that it is a classification. Then the second step may be to find out what kind of algorithm to use. Now, since this is a binary classification problem, logistic regression is a very common algorithm. But however, right, as I said earlier also, we can never say that, okay, for this particular problem, this is exactly the algorithm that we can use. So we can also probably try decision trees or even support vector machines, for example, SVM. So we will kind of list down a few of these algorithms and we will say, okay, we would like to try out these algorithms. And then we go about taking your historical data, which is the labeled data, which are marked. So you will have a bunch of emails, and then you split that into training and test data sets. You use your training data set to train your model or your algorithm that you have used, or rather the model actually. So, and you actually will have three models. Let's say you are trying to test out three algorithms, so you will obviously have three models. So you need to try all three models and test them out as well, see which one gives the best accuracy, and then you decide that you will go with that model. Okay, so training and test will be done, and then you zero in on one particular model, and then you say, okay, this is the model we will use, and then go ahead and implement that or put that in production. So that is the way you design a spam filter. The next question is about random forest. So what is random forest? So this is a very straightforward question. However, the response, you need to be again a little careful. While we all know what is random forest, explaining this can sometimes be tricky. So one thing is, random forest is kind of, in one way, it is an extension of decision trees, because it is basically nothing but you have multiple decision trees, and trees will basically we will use for doing, if it is classification, mostly it is classification, you will use the trees for classification, and then you use voting for finding the final class. So that is the underlying. But how will you explain this? How will you respond to this? So first thing, obviously, we will say that random forest is one of the algorithms, and the more important thing that you need to, probably the interviewer is waiting to hear, is ensemble learner, right? So this is one type of ensemble learner. What is ensemble learner? Ensemble learner is like a combination of algorithms. So it is a learner which consists of more than one algorithm or more than one maybe models. Okay, so in case of random forest, the algorithm is the same, but instead of using one instance of it, we use multiple instances of it, and we use. So in a way, that is a random forest is an ensemble learner. There are other types of ensemble learners where we have, like, we use different algorithms itself. So you have one maybe logistic regression and a decision tree combined together, and so on and so forth. Or there are other ways, like for example, splitting the data in a certain way and so on. So that's all about ensemble. We will not go into that, but random forest itself, I think the interviewer will be happy to hear this word ensemble learner. And so then you go and explain how the random forest works. So if the random forest is used for classification, then we use what is known as a voting mechanism. So basically, how does it work? Let's say your random forest consists of 100 trees, okay, and each observation you pass through this forest, and each observation, let's say it is a classification problem, binary classification 0 or 1, and you have 100 trees. Now, if 90 trees say that it is a 0 and 10 of the trees say it is a 1, you take the majority. You may take a vote, and since 90 of them are saying 0, you classify this as 0. Then you take the next observation and so on. So that is the way random forest works for classification. If it is a regression problem, it's somewhat similar, but only thing is, instead of vote, what we will do is, so in regression, remember what happens? You actually calculate a value. Right? So, for example, you're using regression to predict the temperature, and you have 100 trees, and each tree obviously will probably predict a different value of the temperature. They may be close to each other, but they may not be exactly the same value. So these 100 trees. So how do you now find the actual value, the output for the entire forest, right? So you have outputs of individual trees which are a part of this forest, but then you need to find the final output of the forest itself. So how do you do that? So in case of regression, you take like an average or the mean of all the 100 trees, right? So this is also a way of reducing the error. So maybe if you have only one tree, and if that one tree makes an error, it is basically 100% wrong or 100% right? But if you have, on the other hand, if you have a bunch of trees, you are basically mitigating that error, reducing that error. Okay, so that is the way random forest works. So the next question is, considering the long list of machine learning algorithms, how will you decide on which one to use? So once again, here there is no way to outright say that this is the algorithm that we will use for a given data set. This is a very good question, but then the response has to be like, again, there will not be a one size fits all. So we need to, first of all, you can probably shorten the list in terms of by saying, okay, whether it is a classification problem or it is a regression problem. To that extent, you can probably shorten the list, because you don't have to use all of them. If it is a classification problem, you only can pick from the classification algorithms, right? So for example, if it is a classification, you cannot use linear regression algorithm there. Or if it is a regression problem, you cannot use SVM, or maybe, no, you can use SVM, but maybe a logistic regression, right? So to that extent, you can probably shorten the list, but still you will not be able to 100% decide on saying that this is the exact algorithm that I'm going to use. So the way to go about is you choose a few algorithms based on what the problem is. You try out your data, you train some models of these algorithms, check which one gives you the lowest error or the highest accuracy, and based on that, you choose that particular algorithm. Okay. All right. Then there can be questions around bias and variance. So the question can be, what is bias and variance in machine learning? So you just need to give out a definition for each of these. For example, bias in machine learning, it occurs when the predicted values are far away from the actual value. So that is a bias. Okay. And whereas they are all the values are probably, they are far off, but they are very near to each other though. The predicted values are close to each other, right? While they are far off from the actual value, but they are close to each other. You see the difference? So that is bias. And then the other part is your variance. Now variance is when the predicted values are all over the place, right? So if the variance is high, that means it may be close to the target, but it is kind of very scattered. So the predicted values are not close to each other, right? In case of bias, the predicted values are close to each other, but they are not close to the target. But here they may be close to the target, but they may not be close to each other. So they are a little bit more scattered. So that is what in case of a variance. Okay, then the next question is about, again, related to bias and variance. What is the trade-off between bias and variance? Yes, I think this is an interesting question because these two are heading in different directions. So for example, if you try to minimize the bias, variance will keep going high. And if you try to minimize the variance, bias will keep going high. And there is no way you can minimize both of them. So you need to have a trade-off saying that, okay, this is the level at which I will have my bias and this is the level at which I will have variance. So the trade-off is that pretty much that you decide what is the level you will tolerate for your bias and what is the level you will tolerate for variance, and a combination of these two in such a way that your final results are not way off. And having a trade-off will ensure that the results are consistent, right? So that is basically the output is consistent, and which means that they are close to each other, and they are also accurate. That means they are as close to the target as possible, right? So if either of these is high, then one of them will go off the track. Define precision and recall. Now again here I think it would be best to draw a diagram and take the confusion matrix, and it is very simple. The definition is like a formula. Your precision is true positive by true positive plus false positive, and your recall is true positive by true positive plus false negative. Okay, so that's, you can just show it in a mathematical way. That's pretty much that can be shown. That's the easiest way to define. So the next question can be about decision tree. What is decision tree pruning and why is it? So basically decision trees are really simple to implement and understand, but one of the drawbacks of decision trees is that it can become highly complicated as it grows, right? And the rules and the conditions can become very complicated, and this can also lead to overfitting, which is basically that during training you will get 100% accuracy, but when you're doing testing you will get a lot of errors. So that is the reason pruning needs to be done. So the purpose or the reason for doing decision tree pruning is to reduce overfitting or to cut down on overfitting. And what is decision tree pruning? It is basically that you reduce the number of branches, because as you may be aware, a tree consists of the root node, and then there are several internal nodes, and then you have the leaf nodes. Now if there are too many of these internal nodes, that is when you face the problem of overfitting, and pruning is the process of reducing those internal nodes. Alright, so the next question can be, what is logistic regression? So basically logistic regression is one of the techniques used for performing classification, especially binary classification. Now there is something special about logistic regression, and there are a couple of things you need to be careful about. First of all, the name is a little confusing. It is called logistic regression, but it is used for classification. So this can be sometimes confusing, so you need to probably clarify that to the interviewer if it's really, if it is required. And they can also ask this like a trick question, right? So that is one part. Second thing is the term logistic has nothing to do with the usual logistics that we talk about, but it is derived from log. So that the mathematical derivation involves log, and therefore the name logistic regression. So what is logistic regression and how is it used? So logistic regression is used for binary classification, and the output of a logistic regression is either a 0 or a 1, and it varies. So it's basically, it calculates a probability between 0 and 1, and we can set a threshold that can vary. Typically it is 0.5. So any value above 0.5 is considered as 1, and if the probability is below 0.5, it is considered as 0. So that is the way we calculate the probability, or the system calculates the probability, and based on the threshold it sets a value of 0 or 1, which is like a binary classification, 0 or 1. Okay, then we have a question around k nearest neighbor algorithm. So explain k nearest neighbor algorithm. So first of all, what is a k nearest neighbor algorithm? This is a classification algorithm. So that is the first thing we need to mention. And we also need to mention that the k is a number. It is an integer. And this is variable, and we can define what the value of k should be. It can be 2, 3, 5, 7, and usually it is an odd number. So that is something we need to mention. Technically, it can be even number also, but then typically it would be odd number, and we will see why that is. Okay. So based on that, we need to classify objects. Okay, we need to classify objects. So again, it will be very helpful to draw a diagram. If you're explaining, I think that will be the best way. So draw some diagram like this, and let's say we have 3 clusters or 3 classes existing, and now you want to find for a new item that has come, you want to find out which class this belongs to, right? So you go about, as the name suggests, you go about finding the nearest neighbors, right? The points which are closest to this, and how many of them you will find, that is what is defined by k. Now let's say our initial value of k was 5. Okay. So you will find the 5 nearest data points. So in this case, as it is illustrated, these are the 5 nearest data points. But then all 5 do not belong to the same class or cluster. So there are one belonging to this cluster 1, the second one belonging to this cluster 2, 3 of them belonging to this third cluster. Okay. So how do you decide? That's exactly the reason we should, as much as possible, try to assign an odd number so that it becomes easier to assign this. So in this case, you see that the majority, actually, if there are multiple classes, then you go with the majority. So since 3 of these items belong to this class, we assign, which is basically the, in this case, the green or the tennis or the third cluster, as I was talking about. Right? So we assign it to this third class. So in this case, it is that's how it is decided. Okay. So k nearest neighbors. So first thing is to identify the number of neighbors that are mentioned as k. So in this case, it is k is equal to 5. So we find the 5 nearest points, and then find out of these 5 which class has the maximum number in that. Okay. And then the new data point is assigned to that class. Okay, so that's pretty much how k nearest neighbors work.
We have reached the end of this session on the machine learning full course. Should you have any questions in mind, need any assistance in your learning journey, or looking for resources like the PPT, project code, and other resources used in this session, please let us know in the comment section below, and our team of experts will be happy to help you at the earliest. Until next time, thank you, stay safe, and keep learning. Stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.